Looking at the path we've traced so far, we arrive at something that feels almost inevitable. Exponentials have threaded through everything, sometimes visible, sometimes hiding beneath other structures. Now we turn to face them directly, to see what they reveal when we stop treating them as tools, and start treating them as landscapes worth exploring on their own terms. The exponential function sits at a strange intersection. It's growth incarnate, the mathematical expression of compounding, of things building on themselves. Start with 1, multiply by some base repeatedly, and you get exponential growth. 1 becomes 2, becomes 4, becomes 8. The pattern is relentless, mechanical even, yet it describes so much of what happens in the world. Populations grow exponentially when resources are unlimited. Radioactive decay follows exponential curves downward. Money compounds. Epidemics spread. The pattern appears everywhere we look. But there's something deeper happening. The exponential function isn't just about repeated multiplication. It's the unique function that equals its own derivative, the function that changes at a rate proportional to its current value. This property makes it fundamental to calculus, to differential equations, to any situation where how fast something changes depends on how much of it there is. When we write e raised to x, we're invoking a specific base, the number e, approximately 2.71828. This number appears naturally when we ask what base makes the derivative of the exponential function equal to the function itself. With any other base, say 2 raised to x, the derivative is a constant multiple of the function. Only with base e does that constant equal exactly 1. The number e itself emerges from a limit. Consider the expression 1 plus 1 over n raised to the n power. As n grows, this expression approaches e. When n equals 1, we get 2. When n equals 10, we get about 2.59. When n equals 100, we get about 2.705. The limit as n goes to infinity is e exactly. This limit has a beautiful interpretation. Imagine interest compounding on the loan. If the annual interest rate is 100%, and it compounds once per year, you get 1 plus 1 equals 2 times your original amount. If it compounds twice per year at 50% each time, you get 1 plus 1/2 squared equals 2.25. If it compounds n times per year at 1 over n per period, you get 1 plus 1 over n raised to n. As the compounding becomes continuous, happening every instant rather than at discrete intervals, the growth factor approaches e. So e is the natural base for continuous compounding. It's what you get when growth is perfectly smooth, when changes happen infinitesimally, rather than in chunks. This makes it the right base for modeling continuous processes, which is most of what we actually care about in science and engineering. The function e raised to x has remarkable properties beyond being its own derivative. It's always positive, never crossing 0. As x goes to negative infinity, the function approaches 0 from above. As x goes to positive infinity, it grows without bound. The curve is smooth, increasing everywhere, ending upward in that characteristic exponential curve. We can extend the exponential to complex numbers. What does e raised to I mean, where I is the square root of -1? Euler's formula provides the answer. E raised to I times theta equals cosine theta plus I times sine theta. This connects the exponential function to trigonometry in a profound way. When theta equals pi, we get e raised to I times pi equals cosine pi plus I times sine pi equals -1 plus 0 equals -1. Rearranging gives e raised to I times pi plus 1 equals 0. Euler's identity, often called the most beautiful equation in mathematics. It links 5 fundamental constants, e, I, pi, 1, and 0. This complex exponential rotates around the unit circle in the complex plane. As theta increases, e raised to I times theta traces a circle of radius 1, moving counterclockwise. The exponential function, which seemed purely about growth, becomes about rotation when we pass to complex numbers. For general complex e equals x plus I times y, we have e raised to z equals e raised to x times y equals e raised to x times c raised to I times y equals e raised to x times the quantity cosine y plus I times sine y. The magnitude is e raised to x, depending only on the real part. The phase is y, depending only on the imaginary part. The complex exponential separates growth from rotation. This makes the exponential function the right tool for describing oscillations. The damped oscillation, something vibrating while gradually losing energy, has the form e raised to negative a times t times cosine omega times t, where a is the damping coefficient and omega is the frequency. We can write this using complex exponentials. as the real part of e raised to negative a plus I times omega times t. Differential equations governing oscillating systems naturally involve exponentials. The equation for a harmonic oscillator, d squared x over dt squared plus omega squared x equals 0, has solutions that are sines and cosines, but these are really just combinations of e raised to I times omega times t and e raised to negative I times omega times t, and e raised to negative I times omega times t. The exponential form often makes calculations cleaner. When we add damping, getting d squared x over dt squared plus 2 times b x dn's dt plus omega squared x equals 0, the solutions involve exponentials multiplied by exponentials. If b is less than omega, we get damped oscillations, e raised to negative b times t times cosine square root of omega squared minus b squared times t. If b equals omega, we get critical damping, a pure exponential decay without oscillation. If b is greater than omega, we get overdamping, a sum of two exponentials with different decay rates. All of these behaviors emerge from the fundamental property that exponentials are eigenfunctions of differentiation. When we assume a solution of the form e raised to lambda times t and substitute into the differential equation, we get an algebraic equation for lambda. Solving that algebraic equation tells us which exponentials appear in the solution. This eigenfunction property extends to partial differential equations. The heat equation, describing how temperature diffuses through a material, is dt over dt equals alpha times d squared t over dx squared. Separating variables, assuming t of x and t equals x of times tau of t, we get tau equals e raised to negative alpha times k squared times t, and x is a combination of sines and cosines, with spatial frequency k. The general solution is a sum over all frequencies, each frequency decaying exponentially in time, at a rate proportional to its square. High frequencies die out quickly, low frequencies persist. Eventually everything smooths to a uniform temperature. The wave equation, d squared u over dt squared equals c squared times d squared u over dx squared, has solutions that combine exponentials differently. We get u of x, then t, proportional to e raised to I times k, times x times e raised to plus or minus I times omega times t, or omega equals c times k. These are traveling waves, patterns moving through space at speed c. Both equations, heat and wave, have exponentials at their core. The difference is whether time appears linearly or quadratically in the equation. Linear time gives oscillation and propagation. Quadratic time gives diffusion and decay. Now consider what happens when we compose exponentials with themselves. The function e raised to x is one such composition. We could also consider e raised to x is one such composition, or x, or any more variations. Each creates different behavior. The function e raised to x grows faster than any polynomial, faster than any single exponential, faster than anything we can easily imagine. When x equals 0, the value is e raised to 1, which is e. When x equals 1, the value is e raised to e, roughly 15.15. When x equals 2, the value is e raised to e squared, roughly 17,000. When x equals 3, we're already in the millions. This is sometimes called double exponential growth or tetration of order 2. It makes ordinary exponential growth look almost linear by comparison. In practical terms, such functions rarely appear in physics, because nothing in the real world can grow that fast for long. But they appear in complexity theory, in certain combinatorial problems, in places where we're counting abstract possibilities, rather than physical quantities. The derivative of e raised to x involves the chain rule. We get e raised to x times e raised to x. The inner function e raised to x has derivative e raised to x. The outer function e raised to u has derivative e raised to u. To multiply them together, the result is e raised to x times e raised to x, which we can also write as e raised to the quantity x plus e raisedness. This derivative is itself growing double exponentially. It grows even faster than the original function in a certain sense. The ratio of the derivative to the function is e raised to x, which is increasing exponentially. This means the function is accelerating exponentially. Not only is it growing, but the rate at which it's growing is itself growing exponentially. Higher derivatives compound this effect. Second derivative is e raised to x times e raised to x, times the quantity 1 plus e raised to x. The third derivative involves more terms, all growing at comparable rates. Each differentiation multiplies by another factor, that's roughly e raised to x, for large x. Integrating e raised to x, as we've noted before, produces no elementary closed form. The antiderivative must exist as a matter of calculus, but cannot be expressed using familiar functions. We can write it as the integral from 0 to x of e raised to t with respect to t, which is correct, but doesn't simplify further. We could expand as a Taylor series and integrate term by term. The series for e raised to x starts with e raised to 1 plus e raised to 1 times the quantity x minus 1 plus e raised to 1 times the quantity x minus 1 squared, over 2 factorial plus e raised to 1 times the quantity 2, plus 1 times the quantity x minus 1 cubed over 3 factorial. The pattern continues growing more complex. Integrating term by term gives us a series for the antiderivative. The constant term e raised to 1 integrates to e raised to 1 times x. The linear term e raised to 1 times the quantity x minus 1 integrates to e raised to 1 times the quantity x minus 1 squared over 2. Each term integrates straightforwardly as a polynomial in x minus 1. This series representation is valid in some neighborhood of x equals 1. It converges for x near 1, though how near depends on the function's behavior. For large x, the series doesn't help much because the convergence is too slow. We'd need other methods, asymptotic expansions or numerical integration, to evaluate the antiderivative far from the expansion point. The broader lesson is that composition creates complexity. The exponential function by itself is tractable, well understood, easy to work with, but nesting exponentials, even once, produces something qualitatively more difficult. Twice tripling exponentials to create e raised to x makes things even worse. There's a hierarchy of growth rates. Polynomials grow according to their degree. Linear functions grow slowest, then quadratic, cubic, and so on. Exponentials grow faster than any polynomial. Double exponentials grow faster than any single exponential. Triple exponentials faster still. This hierarchy continues indefinitely. At the other end, inverse functions decay instead of grow. The natural logarithm, the inverse of the exponential, grows slower than any positive power of x. The function log x grows slower still. These ultra-slow growing functions appear in complexity theory, measuring how efficiently certain algorithms perform. Between growth and decay sits a balance point. Functions that grow exactly fast enough to stay bounded, but not so slow as to go to zero. These are the borderline cases, often the most interesting. They include things like x raised to the 1 over x power, which peaks at x equals e, and then slowly decreases. The exponential function's domain and range are worth examining closely. For real numbers, the domain is all real x, and the range is all positive real numbers. Every positive number can be expressed as e raised to something. If you want to get 10, you raise e to the natural log of 10, which is about 2.303. If you want 1/2, you raise e to negative natural log of 2, which is about negative 0.693. The natural logarithm is the inverse function of the exponential. It undoes exponentiation. If y equals e raised to x, then x equals natural log of y. The logarithm takes positive numbers and returns their exponents. It converts multiplication into addition. The natural log of a times b equals natural log of a plus natural log of b. This property makes logarithms useful for understanding multiplicative processes. The graph of natural log of x is the reflection of e raised to x across the line y equals x. It passes through the point 1, 0, since e raised to 0 equals 1. It increases everywhere but very slowly. As x approaches infinity, natural log of x approaches infinity too, but much more gradually than x itself grows. The derivative of natural log of x is 1 over x. This inverse relationship, where the exponential's derivative is itself, and the logarithm's derivative is 1 over the input, reflects their inverse nature. Composing them in either order gives the identity function, at least when domains are respected. For complex numbers, both functions become multi-valued, or require branch cuts. The exponential e raised to z is single-valued for complex z, taking every non-zero complex value infinitely many times, due to the periodicity in the imaginary direction. But the logarithm of a complex number is not unique. If z equals e raised to w, then z also equals e raised to w plus 2 pi I times n, for any integer n. We choose a principal branch of the logarithm, typically taking the imaginary part, between negative pi and pi. This makes log single valued on the complex plane, minus the negative real axis. But crossing that branch cut causes the logarithm to jump discontinuously. This is a general feature of inverse functions in the complex plane. They tend to be multi-valued unless we restrict their domains carefully. The square root has 2 values, the cube root 3 values, the nth root n values. The logarithm has infinitely many values, spaced 2 pi I apart. These multiple values are not errors or ambiguities. They're genuine features of the complex structure. Each value is equally valid mathematically. Which one we use depends on context, on which branch we've chosen to work with. The complex exponential connects to power series in a direct way. We've written e raised to z equals the sum from n equals 0 to infinity of z to the n over n factorial. This series converges for all complex z, making the exponential an entire function, analytic everywhere in the complex plane. The radius of convergence is infinite. No matter how large z gets, the series still converges, because factorials in the denominators grow faster than any polynomial in the numerator. This rapid growth of factorials ensures convergence. Other exponential type functions have finite radii of convergence. The function 1 over the quantity 1 minus z equals the sum from n equals 0 to infinity of z to the n converges only for the magnitude of z less than 1. This geometric series diverges outside the unit circle. The 1 over 1 minus z is a rational function, not an exponential. Its singularity at z equals 1 prevents it from being entire. The exponential has no singularities anywhere in the finite complex plane. Its only singularity is at infinity, and that's an essential singularity, a point where the function's behavior is maximally wild. Near an essential singularity, an analytic function takes on every complex value, infinitely often, in every neighborhood, with at most one exception. For the exponential, the exception is 0. Every other complex number is achieved infinitely many times near infinity. This is Picard's great theorem, a remarkable result. It says that essential singularities are truly singular, fundamentally different from poles or removable singularities. The function doesn't just blow up, it thrashes around in the complex plane, hitting almost everything infinitely many times. For e raised to z, the behavior is even more extreme. This function also has an essential singularity at infinity, and it too takes on every complex value except 0 infinitely many times near infinity. But because it's a composition of exponentials, its behavior is doubly wild in some sense. The modulus, the absolute value of e raised to z, depends on the real part of e raised to z. If z equals x plus I times y, then e raised to z equals e, placed to x times e raised to I times y, with modulus e raised to x. So e raised to z has modulus e raised to x times cosine y. For fixed x, as y varies, cosine y oscillates between -1 and 1. So e raised to x times cosine y varies between negative e raised to x and e raised to x, meaning the modulus of e raised to e raised z varies between e raised to negative e raised to x and e raised to e raised to x. This is an enormous range once x is even moderately large. When x equals 3, e raised to x is about 20, so the modulus varies between e raised to -20, which is tiny, and e raised to 20, which is huge. The function oscillates wildly in magnitude as we move in the imaginary direction. The phase, the argument of e raised to z, is similarly complex. It depends on the imaginary part of e raised to z, which is e raised to x times sine y. This winds around as y increases, creating spiraling behavior in the complex plane. Visualizing this function requires thinking carefully about what we want to see. We could plot the magnitude as a surface over the complex plane, watching it grow and oscillate. We could use color to represent phase, creating a domain coloring. We could trace curves where the magnitude is constant, or where the phase is constant. Each visualization reveals different aspects. The magnitude plot shows the exponential growth in certain directions, and the oscillation in others. The phase plot shows the winding and spiraling. Together they give a sense of the function's rich structure. But no single picture captures everything. This is a function from 2 real dimensions, the complex plane, to 2 more real dimensions, the complex output. We're trying to visualize 4-dimensional information, which requires choices about what to project or slice or color. One approach is to fix the imaginary part of the input, then plot the output as the real part varies. Or fix the real part, then vary the imaginary part. Or trace the image of various curves in the input plane. Each choice gives partial information. The exponential function's collection to differential equations extends far beyond simple examples. Consider the matrix exponential, defined for square matrices in analogy with the scalar exponential. If A is a matrix, we define e raised to a as the sum from n equals 0 to infinity of a to the n, power over n factorial. This series converges for any matrix, just as the scalar series converges for any complex number. The matrix exponential has properties similar to the scalar exponential. If a and b commute, meaning a times b equals b times a, then e raised to a plus b equals e raised to a times e raised to b. The matrix exponential is the solution to systems of linear differential equations of constant coefficients. If dy over dt equals a times y, or y is a vector and a is a constant, matrix the solution is y of t equals e raised to a times y of 0. To compute e raised to a times t, we can diagonalize a if possible, finding matrices p and d such that a equals p times d times b inverse, where d is diagonal. Then a to the n equals p times d to the n times p inverse. And the series for e raised to a becomes e raised to a equals p runs to e times t inverse to c. D is diagonal. Since d is diagonal, e raised to a is just the diagonal matrix with e raised to each diagonal entry of d. This reduces the matrix exponential to scalar exponentials of the eigenvalues. If a can't be diagonalized, we use the Jordan normal form, which is almost diagonal, with ones just above the diagonal in certain places. The exponential of a Jordan block involves not just exponentials, but also polynomials times exponentials. All of this machinery exists to solve differential equations. The abstract structure mirrors the concrete calculations we do for scalar equations. Eigenvalues of the matrix play the role of the constants lambda in scalar equations. Eigenvectors give the direction of exponential growth or decay. In physics, these matrix exponentials describe quantum time evolution. Schrödinger equation, I times d psi over dt equals h times psi, as solution psi of t equals e raised to negative I times h times t times psi of 0, where h is the Hamiltonian operator. For finite-dimensional systems, this is a matrix exponential. The Hamiltonian's eigenvalues are the energy levels. The eigenvectors are the stationary states. The time evolution operator e raised to negative I times h times t rotates the state vector in Hilbert space, creating the dynamics of quantum mechanics. So exponentials are not just mathematical abstractions. They describe how systems evolve in time, how waves propagate through space, how quantum states interfere and decohere. They're the functions of change, of dynamics, of becoming. Let's return to growth rates and comparisons. We've said exponentials grow faster than polynomials. More precisely, for any polynomial p of x and any exponential e raised to a times x with a positive, the ratio e raised to a times x over p of x goes to infinity as x goes to infinity. This means that eventually, no matter how large the degree of the polynomial or how large its coefficients, the exponential overtakes it and grows faster. The polynomial might leave for mean a while if it has huge coefficients or very high degree, but asymptotically exponential wins. Similarly, logarithms grow slower than any positive power. The ratio natural log of x over x raised to epsilon goes to 0, as x goes to infinity, for any epsilon greater than 0, no matter how small. Logarithms grow, but barely, compared to power functions. Between polynomials and exponentials sits a rich landscape of intermediate growth rates. Functions like x raised to natural log of x, which is also e raised to natural log of x, times natural log of x, grow faster than any polynomial, but slower than any exponential. These superpolynomial but sub-exponential functions appear in complexity theory, particularly in factoring algorithms. There are even finer distinctions. The function e raised to the square root of natural log of x grows faster than any polynomial, but slower than any exponential. It's in a class called sub-exponential. Algorithms with this running time are faster than exponential but not polynomial. The hierarchy of growth rates is densely ordered. Between any two growth rates, we can find infinitely many intermediate ones. This makes classification tricky. Resort to asymptotic notation, saying a function is big O of another if it grows at most as fast, or big omega if at least as fast, or big theta if they grow at the same rate up to constant factors. These notations let us compare algorithms and functions without getting bogged down in exact formulas. We care about long-term behavior, about what happens as inputs get large, not about small inputs where everything is fast anyway. Exponentials also appear in probability and statistics. The normal distribution, the bell curve, has probability density proportional to e raised to negative f squared over 2. This exponential of a quadratic creates the characteristic shape, peaking at 0 and falling off rapidly in both directions. The normal distribution is ubiquitous because of the central limit theorem. Sums of many independent random variables, regardless of their individual distributions, tend toward normality as the number of terms increases. The exponential function emerges from this limiting process. Other distributions involve exponentials too. The exponential distribution itself, used to model waiting times, has density a times e raised to negative a times x for a is positive. The Poisson distribution, counting rare events, has probabilities e raised to negative lambda times lambda to the k over k factorial. Exponentials and their relatives pervade probabilistic models. In information theory, the exponential appears in the definition of entropy and encoding theorems. If a message has probability p of occurring, its information content is negative natural log of p. Summing over all messages weighted by their probabilities gives entropy. The connection to exponentials is that entropy measures the exponent in the number of typical sequences. If we have n independent uses of a channel with entropy h, there are roughly 2 raised to n times h typical sequences. The exponential function converts entropy to account. Maximum entropy distributions, those that make the fewest assumptions given constraints, often involve exponentials. If we know only the mean, the maximum entropy distribution is exponential. If we know the mean and variance, it's normal. These distributions maximize randomness subject to what we know. Shannon's noisy channel coding theorem says we can communicate reliably at any rate below channel capacity by using exponentially long codes. The probability of error goes to 0, exponentially fast in the code length. Exponentials govern how quickly we can make communication reliable. Now consider the function e raised to negative x. This is a decreasing exponential, approaching 0 as x goes to infinity, and approaching infinity as x goes to negative infinity. It's the mirror image of e raised to x, reflected across the vertical axis. Decreasing exponentials model decay processes. Radioactive decay follows this pattern. If you start with some amount of a radioactive substance, after time t, you have the original amount times e raised to negative lambda times t, where lambda is the decay constant. Half-life is the t when this equals 1/2, which occurs at t equals natural log of 2 over lambda. Cooling also follows exponential decay. Newton's law of cooling says the temperature difference between an object and its surroundings decreases exponentially over time. If T of t is temperature, and T sub s is surrounding temperature, then T of t minus T sub s equals the quantity T of 0 minus T sub s times e raised to negative k times t. Charging and discharging capacitors, drug concentrations in the bloodstream, atmospheric pressure, as a function of altitude all follow exponential patterns, some increasing, some decreasing, all reflecting a fundamental property that the rate of change is proportional to the current amount. The function e raised to negative x squared, without the division by 2, is the unnormalized Gaussian. Its integral from negative infinity to infinity is the square root of pi, a famous result. To normalize it, we divide by this integral, giving 1 over the square root of 2 pi times e raised to negative x squared over 2. This function decays faster than any exponential of x alone, because the exponent grows quadratically rather than linearly. It's sometimes called superexponential decay. By the time x reaches 3 or 4, the value is already negligibly small. Such rapid decay makes the Gaussian convenient for analysis. Almost all the probability mass sits near the center. Tails are negligible. We can truncate integrals at a few standard deviations without significant error. The Gaussian also has the nice property that its Fourier transform is another Gaussian. The transform of e raised to negative x squared is proportional to e raised to negative omega squared over 4. Self-similarity under Fourier transform makes Gaussian special, connecting time and frequency domains in a symmetric way. In quantum mechanics, Gaussian wave packets are the minimum uncertainty states, saturating the Heisenberg uncertainty principle. They're as localized as quantum mechanics allows, balancing position and momentum uncertainties. Multiplying 2 Gaussians gives another Gaussian. Convolving 2 Gaussians gives a Gaussian with variance, equal to the sum of the original variances. These closure properties make Gaussian processes mathematically tractable. But let's return to compositions and nestings. We've discussed e raised to x. What about x raised to x? This is also a super exponential function, though defined differently. For positive x raised to x equals e raised to x times natural log of x. As x increases from 0, x raised to x starts at the limit value 1, which requires some care to define. We take the limit as x approaches 0 from above, of x raised to x equals the limit of e raised to x times natural log of x. As x approaches 0, natural log of x goes to negative infinity, but x times natural log of x goes to 0. So the limit is e raised to 0 equals 1. The function x raised to x decreases slightly from 1, reaching a minimum around x equals e to the negative 1, where the value is about 0.692. Then it increases, growing faster than any exponential, but slower than e raised to x. The derivative of x raised to x uses the technique of logarithmic differentiation. Let y equals x raised to x. Take the natural log of both sides. Natural log of y equals x times natural log of x. Differentiate both sides with respect to x. The left side gives 1 over y times dy over dx. The right side gives natural log of x plus x times 1 over x equals natural log of x plus 1. So 1 over y times dy over dx equals natural log of x plus 1, which means dy over dx equals y times the quantity natural log of x plus 1 equals x raised to x times the quantity natural log of x plus 1. This derivative is positive for x greater than e to the negative 1, confirming the function increases after its minimum. At large x, the derivative grows like x raised to x times natural log of x, which is nearly as fast as the function itself, indicating rapid growth. The function x raised to x is even more extreme. Here we have a tower of height 3. Evaluating at x equals 2 gives 2 raised to 2 raised to 2 equals 2 raised to 4 equals 16. At x equals 3, we get 3 raised to 3 raised to 3 equals 3 raised to 27, which is already in the trillions. Such rapidly growing functions appear in combinatorics, in counting certain structures or configurations. They also appear in theoretical computer science, measuring the complexity of certain algorithms, or the resources needed to solve certain problems. The inverse of these functions, the superlogarithms, or iterative logarithms, grow incredibly slowly. The function log star of x, the number of times you need to apply logarithm to reduce x to 1 or less, grows so slowly it might as well be constant for practical purposes. For x up to e raised to e raised to e raised to e, we have log star of x, at most 5. These ultra-slow growing functions appear in algorithm analysis. Some algorithms have running time proportional to n times log star of n, which is essentially linear for any realistic n. The log star is theoretically present but practically invisible. Between the extremes of super-exponential growth and super-logarithmic slowness lies the realm where most interesting functions live. Linear, quadratic, cubic growth, exponential, logarithmic, square root. These are the functions we encounter in applications, the ones that model real phenomena at human scales. But the extreme functions remind us of the breadth of possibility. Mathematics contains functions growing and decaying at every conceivable rate. The hierarchy is rich and infinite. No matter how fast a function grows, we can construct one that grows faster. No matter how slowly, we can construct one slower. This open-endedness is part of what makes mathematics inexhaustible. There's always something beyond what we've considered. Always another level of complexity or simplicity to explore. Let's think about the exponential from yet another angle, through generating functions. The generating function encodes a sequence as a power series. If we have sequence a 0, a 1, a 2, and so on, the generating function is the sum from n equals 0 to infinity of a sub n times x to the n. For the sequence of all 1s, 1, 1, 1, 1, the generating function is the sum of x to the n, which equals 1 over 1 minus x for the magnitude. At x less than 1, this geometric series is the simplest generating function. For the sequence in factorial, we get the sum of n factorial times x to the n. This series doesn't converge for any x not equal to 0 in the usual sense, but we can work with it formally, manipulating it algebraically without worrying about convergence. The exponential generating function of a sequence uses x to the n over n factorial, instead of just x to the n. For the sequence a sub n, this is the sum of a subs m times x to the n over n factorial. The exponential generating function of the sequence of all 1s is the sum of x to the n over n factorial equals e raised to x. So the exponential generating function of the sequence is all 1, 1, 1. This connects the functions at combinatorics, The nth coefficient, divided by n factorial, counts something related to permutations or arrangements. For the sequence in factorial, the exponential generating function is the sum of n factorial times x to the n over n factorial equals the sum of x to the n equals 1 over 1 minus x. So the ordinary generating function of factorials doesn't converge, but their exponential generating function is simple. These generating functions let us solve recurrence relations, count combinatorial objects, and translate between different representations of sequences. The exponential function appears whenever we're counting labeled structures, where the order of elements matters. In graph theory, the exponential generating function of connected graphs on n-labeled vertices involves the exponential function. The function e raised to x times the quantity e raised to e raised to x minus 1 minus x appears in formulas for counting various graph properties. These applications might seem far from the original conception of exponentials as growth functions, but they're united by the underlying mathematics. The exponential encodes information about factorials, about repeated operations, about structure building on itself. We could also discuss the exponential function's role in Fourier analysis more deeply. The Fourier transform takes a function f of x and produces the function f of omega equals the integral from negative infinity to infinity of f of x times e raised to negative I times omega times x with respect to x. This transform decomposes f into its frequency components. The function e raised to negative I times omega times x oscillates at frequency omega. Integrating f times this oscillation gives the amplitude of that frequency in f. The inverse Fourier transform reconstructs f from its frequency components. F of x equals 1 over 2 pi times the integral of f of omega times e raised to I times omega times x with respect to omega. These transforms are inverse to each other, up to constants. They convert between time and frequency, between position and momentum, between different representations of the same information. The exponential function, with its dual role as growth function and oscillation, is the kernel that makes this work. It's the eigenfunction of differentiation, the bridge between addition and multiplication via logarithms, the generator of rotations in the complex plane. All these roles stem from the single defining property, being equal to its own derivative. From this, everything else follows. The series expansion, the complex behavior, the connections to differential equations in Fourier analysis, all emerge from that one fact. In a sense, the exponential function is the simplest non-trivial function. Polynomials are simpler, but they don't capture dynamics. Constants are simpler still, but they don't capture change at all. The exponential is the first function that's truly alive, that embodies growth and change in a fundamental way. When we nest exponentials, creating towers of compositions, we're exploring how complexity emerges from simplicity. Each layer adds another level of indirection, another fold in the function's behavior. The result grows faster, oscillates more wildly, becomes harder to analyze. But even the most complex exponential composition is still built from the same simple pieces. It's still differentiable, still analytic where it's defined, still subject to the rules of calculus and complex analysis. The tools we use to understand simple functions still apply, though the calculations become more involved. This is a common pattern in mathematics. We start with simple objects and simple operations. We combine them in increasingly complex ways. The combinations inherit properties from the pieces, but exhibit new emergent behaviors. Understanding both the inheritance and the emergence is the challenge. Exponentials exemplify this pattern. They're simple in isolation, profound in combination, inexhaustible in variation. They connect discrete and continuous, algebraic and analytic, real and complex. They model growth and decay, oscillation and rotation, stability and chaos. In some ways, the entire edifice of calculus rests on exponentials. Derivatives and integrals, series and limits, differential equations and transforms, all involve exponentials at their core. Learning to work with exponentials is learning to work with change itself, and that's what calculus is ultimately about. Understanding how things change, how one quantity depends on another, how small differences accumulate into large effects, how local information determines global behavior. The exponential function, in its own derivative, is the fixed point of differentiation. It's the function that change doesn't change, that remains itself under the operator that measures change. This paradoxical stability, while embodying change, makes it central to the entire subject. As we've seen, even restricting to real numbers, exponentials are rich. Adding complex numbers multiplies that richness. The plane becomes a landscape of growth and rotation, magnitude and phase, zeros and poles, and essential singularities. Generalization opens new vistas. Matrix exponentials for systems of equations. Operator exponentials for quantum evolution. Exponential maps in Lie theory connect to algebra and geometry. The concept extends far beyond the elementary function we started with. Yet all these generalizations preserve the core property. Exponentials are the solutions to equations of the form derivative equals constant times function. In one dimension, scalar equations. In many dimensions, matrix equations. In manifolds, operator equations. The pattern persists across contexts. This universality suggests we're touching something fundamental about mathematics itself, not just about a particular function. The exponential represents something deep about how structures build on themselves, how recursive processes unfold, how symmetry and dynamics intertwine. In the end, studying exponentials is studying the mathematics of becoming, of process, of change. It's looking at the world not as static configurations, but as flows and transformations. This perspective pervades modern mathematics and physics, from dynamical systems to quantum field theory. The function e raised to x, simple as it appears, contains multitudes, its derivatives, its integrals, its series, its values. All tell us something about the nature of growth and change. When we compose it with itself, we see how complexity emerges from iteration. When we apply it to matrices or operators, we see how it organizes higher dimensional dynamics. Every time we encounter an exponential in mathematics, we're meeting an old friend in a new guise. The function might be wearing different clothes, might be playing a different role, but it's the same underlying structure. Recognizing it, understanding its properties, using it effectively, these are core skills in mathematical thinking. And beyond pure mathematics, exponentials shape how we understand the world. Population dynamics, compound interest, radioactive decay, electrical circuits, temperature change, all follow exponential patterns. Learning to recognize and work with these patterns is learning to think quantitatively about change. So while this exploration is focused on mathematical properties, the implications extend far beyond. Exponentials are tools for thought, frameworks for understanding, bridges between abstract theory and concrete application. The journey from e raised to x through e raised to x, and beyond traces a path from elementary to advanced, from simple to complex, from familiar to strange. But it's all continuous, all connected, all part of the same mathematical landscape. Understanding that landscape, being able to navigate it, seeing how different regions connect and differ, that's what mathematical maturity looks like. It's not about memorizing formulas or techniques, though those help. It's about seeing structure, recognizing patterns, understanding why things work the way they do. Exponentials offer a perfect case study in this kind of understanding. They're simple enough to grasp quickly, but deep enough to repay extended study. They appear everywhere, connect to everything, reveal new aspects the longer you look. This text has tried to capture some of that richness, to show exponentials from multiple angles, to trace connections between different appearances of the same underlying idea. The goal isn't exhaustive coverage, which would take volumes. It's to give a sense of the landscape, to point out interesting features, to encourage further exploration. Mathematics is infinite. We can never see all of it, but we can see enough to appreciate its structure, to navigate confidently within familiar regions, to venture into new territories with some idea of what to expect. Exponentials are an excellent region to know well. They're central, well-connected, beautiful in their own right. Spending time here, understanding the terrain, pays dividends throughout mathematics and beyond. As this section closes, the exponential function remains, as it has always been, fundamental and inexhaustible. Each encounter reveals something new. Each application shows another facet. The function that equals its own derivative, that bridges growth and rotation, that solves so many equations and models, so many phenomena, continues to surprise and enlighten. The exponential function rises with a persistence that defies ordinary growth. Where linear increases march forward and steady steps and quadratic curves bend gradually upward, the exponential explodes into territories that seem almost unnatural in their acceleration. To raise a number to a power means to multiply that base by itself repeatedly. And when that power itself grows, when x becomes the exponent rather than the base, we enter realms where intuition stumbles and magnitude becomes almost meaningless. Consider e raised to the power of x, where e represents that mysterious constant approximately equal to 2.71828. This number emerges from the study of continuous growth, from compound interest calculated at every infinitesimal moment, from the derivative that equals its own function. When we write e to the x, we describe a function that at every point grows at a rate proportional to its current value. The slope at any location equals the height at that location. This self-reference creates a feedback loop of increase, a mathematical echo chamber where growth begets more growth. The journey begins gently enough. When x equals -3, e to the power of -3 yields approximately 0.05. The function hugs the horizontal axis, barely distinguishable from 0. Moving rightward, at x equals -2, we find e squared in the denominator, giving roughly 0.14. Still small, still contained. At -1, e to the -1 equals 1 divided by e, approximately 0.37. The curve begins its turn upward. At the origin, where x equals 0, something beautiful occurs. Any number raised to the 0 power equals 1, and e to the 0 is no exception. The function crosses the vertical axis at unity, at the point where horizontal and vertical meet in perfect coordination. This serves as the anchor, the reference point from which all other values derive their meaning. At the positive territory, the transformation accelerates with breathtaking speed. At x equals 1, we simply have e itself approximately 2.72. Already we've nearly tripled from the origin. At x equals 2, e squared gives approximately 7.39. The gap widens. At 3, e cubed reaches roughly 20.09. At 4, we touch 54.6. At 5, 148.4. The distances between consecutive integer values grow exponentially themselves. From 0 to 1, we gain 1.72 units. From 1 to 2, we gain 4.67 units. From 2 to 3, 12.7 units. From 3 to 4, 34.5 units. Each step covers more ground than all previous steps combined, stretched and magnified. This pattern extends infinitely. At x equals 10, e to the 10th reaches 22,000 and change. At 15, over 3 million. At 20, we breach 480 million. The numbers become abstractions, collections of digits that no longer connect to tangible quantities. We speak of billions, trillions, values that dwarf human experience. The inverse relationship holds equal fascination. For negative x values, e raised to -x equals 1, divided by e to the x. This creates a mirror image, a reflection across the vertical axis, where decay replaces growth. The function approaches 0 asymptotically, getting closer and closer, but never quite touching, never reaching that ultimate terminus. At x equals -10, we find a number so small it requires scientific notation to express, meaningfully, approximately 0.00000454. Between these extremes lies the full spectrum of exponential behavior. The continuous nature of e to the x means we can evaluate it at any real number, not just integers. At x equals 1/2, e to the 1/2 equals the square root of e, approximately 1.65. At 3/2 we get roughly 4.48. The function flows smoothly, without breaks or jumps, tracing an elegant curve that sweeps from near 0 on the left to unbounded heights on the right. The derivative of e to the x with respect to x equals e to the x itself. This remarkable property makes the exponential function its own rate of change. If we imagine a particle moving along a path where its velocity at any instant equals its position, we describe exponential motion. The particle accelerates continuously, its speed increasing in direct proportion to how far it has traveled. The self-reinforcing dynamic appears throughout nature. In population growth when resources remain unlimited. In nuclear chain reactions. In the spread of information through social networks. Integration reveals the same pattern. The integral of e to the x, with respect to x equals e to the x, plus an arbitrary constant. The antiderivative matches the original function. This symmetry between differentiation and integration distinguishes the exponential from other elementary functions, creating a mathematical object that remains invariant under the fundamental operations of calculus. We can shift and scale the exponential to create families of related functions. Multiplying by a constant, a gives a times e to the x, which stretches the graph vertically. The y-intercept moves from 1 to a, but the fundamental shape persists. Every point rises or falls by the same factor, preserving the exponential character. Adding a constant to the exponent creates horizontal shifts. The function e raised to the quantity x minus h translates the entire graph h units to the right, if h is positive, or left if h is negative. The zero crossing moves, the point where the function equals 1 relocates, but the essential behavior remains unchanged. We still have exponential growth, just centered at a different location. Multiplying the exponent by a constant k yields e raised to kx, which affects the rate of growth. When k exceeds 1, growth accelerates even faster. When k lies between 0 and 1, growth slows but continues. Negative k produces exponential decay, mirroring growth with decline. These variations allow us to model different scenarios, different speeds of change, while maintaining the core exponential structure. The natural logarithm serves as the inverse of the exponential function. If y equals e to the x, then x equals the natural logarithm of y. This relationship allows us to solve exponential equations, to unpack growth, and find the time required to reach specific values. The logarithm converts multiplication into addition, powers into products, providing tools to linearize exponential relationships and render them more tractable. Compound interest provides a classic application. When money grows at a continuous rate, r, the value at time t equals the initial principal, p times e raised to rt. The exponential captures the effect of constant percentage growth, where each increment builds on everything that came before. A savings account, a viral video, a pandemic spreading through a population, all follow this basic template when unchecked by external constraints. The exponential distribution in probability theory uses e raised to negative lambda x to model waiting times between events in a Poisson process. Here the exponential decay represents the likelihood of longer intervals, with most events occurring relatively quickly, and rare instances stretching far into the future. The memoryless property emerges from the exponential form. The probability of waiting an additional unit of time remains constant, regardless of how long we've already waited. In physics, radioactive decay follows exponential patterns. The number of unstable atoms at time t equals the initial count, times e raised to negative lambda t, where lambda represents the decay constant. Half-life derives from solving for the time when this expression equals 1/2 the original amount, connecting exponential decrease to observable physical phenomena. Temperature equilibration obeys Newton's law of cooling, where the temperature difference between an object and its surroundings decreases exponentially over time. A hot coffee cooling in a room, a frozen dinner thawing on the counter, both trace exponential curves as they approach ambient temperature. The rate of heat transfer at any moment depends on the current temperature gap, creating the self-referential dynamics characteristic of exponential processes. Electrical circuits containing capacitors or inductors exhibit exponential charging and discharging. When a capacitor charges through a resistor, the voltage across the capacitor grows as 1 minus e raised to negative t divided by RC, where RC represents the time constant. The current decays exponentially as the capacitor fills. Discharging reverses the process, with stored energy dissipating, according to an exponential decay law. The catenary curve, the shape assumed by a hanging chain or cable under its own weight, involves hyperbolic cosine, which can be expressed as 1/2 times the sum of e to the x and e to the negative x. This combination of growth and decay creates the graceful arc we see in suspension bridges and power lines, where material properties and gravitational forces find equilibrium in exponential relationships. Probability distributions like the normal distribution, though not purely exponential, incorporate e raised to negative x squared. The Gaussian curve's bell shape arises from exponential decay of the square of the distance from the mean, creating the ubiquitous pattern we find in measurement, errors, natural variations, and countless statistical phenomena. The gamma function, which extends factorial to non-integer values, requires integrating t raised to x minus 1 times e to the negative t from 0 to infinity. The exponential term ensures convergence, taming the polynomial growth, then allowing the integral to exist for positive x values. This interplay between polynomial and exponential behaviors characterizes many special functions in mathematical analysis. Laplace transforms convert differential equations into algebraic equations. By integrating functions multiplied by e raised to negative saint, the exponential weighting privileges certain frequencies, transforming time domain problems into frequency domain solutions, where analysis becomes more straightforward. Engineers use Laplace transforms to study control systems, signal processing, and circuit analysis. The moment-generating function in probability, defined as the expected value of e raised to tx, encodes all moments of a distribution when they exist. Taking derivatives at t equals 0 extracts mean, variance, skewness, and higher moments, providing a compact representation of distributional properties through exponential machinery. Stirling's approximation for large factorials uses exponentials to simplify unwieldy products. For large n, n factorial approximately equals the square root of 2 pi n, times the quantity n divided by e raised to the power n. This exponential approximation makes calculations feasible and reveals the asymptotic behavior of factorial growth. The binomial distribution approaches the Poisson distribution in certain limits, a convergence mediated by exponential functions. When the number of trials grows large, while the probability of success per trial shrinks proportionally, the discrete binomial converges to the continuous Poisson, whose probability mass function involves e raised to negative lambda. In economics, exponential growth models capture idealized market expansions, though real economies face constraints that eventually impose bounds. The assumption of constant percentage returns leads to exponential projections, useful for short-term forecasting, but requiring modification for long-term accuracy. The exponential provides a baseline, a limiting case against which actual growth can be measured. Population models frequently begin with exponential assumptions. Malthusian growth, where population increases proportional to current size, yields exponential solutions. Of course, real populations encounter resource limitations, predation, disease, and other density-dependent factors that modify simple exponential dynamics. The logistic equation introduces carrying capacity, bending exponential growth into an S-curve that saturates at environmental limits. Epidemiological models during the early stages of disease outbreaks often show exponential increase in cases. Each affected individual potentially infects multiple others, creating chains of transmission that multiply geometrically. Public health interventions aim to break these chains, reducing the effective reproduction number below 1, and transforming exponential growth into exponential decay. The mathematics of compound interest demonstrates exponential accumulation of wealth. When interest compounds continuously at rate r, the future value equals the present value times e raised to rt. This explains the power of long-term investing, where time and compound returns interact exponentially to build substantial assets for modest initial contributions. Information theory uses exponential functions in entropy calculations. The Shannon entropy of a discrete probability distribution sums terms of the form negative p times the logarithm of p, where p represents probability. Since logarithms invert exponentials, this formulation quantifies uncertainty through exponential related expressions, measuring the average information content of messages from a source. Thermodynamics employs the Boltzmann distribution, or the probability of a system occupying a state with energy E is proportional to e raised to negative e divided by kT, with k representing Boltzmann's constant and T absolute temperature. Higher energy states become exponentially less likely at lower temperatures, explaining phase transitions and thermal equilibrium. Chemical kinetics relies on the Arrhenius equation, which states that reaction rate constants depend on E raised to negative activation energy divided by RT. Temperature appears in the denominator of the exponent, so higher temperatures exponentially increase reaction rates by allowing more molecules to overcome energy barriers. This exponential sensitivity explains why small temperature changes can dramatically affect reaction speeds. The Black-Scholes model for option pricing incorporates exponential terms in its solution for call input values. The model assumes stock prices follow geometric Brownian motion, with returns distributed log-normally, connecting exponential functions to financial derivatives and risk management. Queuing theory models waiting lines using exponential distributions for arrival times and service durations. The memoryless property simplifies analysis, allowing elegant solutions for average wait times, queue lengths, and system utilization in MM1 and related queues. Survival analysis in medical statistics often assumes exponential or related distributions for time-to-event data. The hazard rate, representing instantaneous risk of failure, can remain constant, exponential, increase or decrease, depending on the underlying distribution chosen to fit observed survival curves. The Poisson process, fundamental to stochastic modeling, generates events randomly in time, with exponentially distributed inter-arrival times. This mathematical idealization approximates many real phenomena. Phone calls arriving at a switchboard, cosmic rays striking a detector, customers entering a store during off-peak hours. Buffon's needle problem, though geometric, connects to exponential functions through probability calculations. The likelihood of a randomly dropped needle crossing parallel lines depends on trigonometric integrals that can be expressed using exponential forms of sine and cosine through Euler's formula. Speaking of Euler's formula, e raised to ix equals cosine x plus I times sine x, uniting exponential, trigonometric, and complex numbers in one stunning equation. This relationship allows us to represent rotations as complex exponentials, simplifying Fourier analysis and signal processing. The exponential spiral in the complex plane traces circles when purely imaginary exponents combine with real-time parameters. Fourier transforms decomposed functions into frequency components, using integrals weighted by e raised to negative 2 pi I times frequency times time. This exponential kernel extracts sinusoidal content at each frequency, transforming temporal patterns into spectral representations essential for audio processing, image analysis, and quantum mechanics. The Schrödinger equation in quantum mechanics is often solved using exponential ansatz. Wave functions frequently involve e raised to ikx for plane waves or e raised to negative r squared for ground state solutions, with exponential behavior reflecting the probabilistic nature of quantum systems and the uncertainty principle's fundamental constraints. Perturbation theory and quantum field theory expands scattering amplitudes in series, involving exponential factors from propagators and interaction vertices. Feynman diagrams encode these exponential contributions, with each term representing quantum mechanical amplitudes that interfere constructively or destructively. The partition function in statistical mechanics sums e raised to negative beta times energy over all possible states, where beta equals 1 divided by kt. This exponential weighting generates thermodynamic quantities through derivatives, connecting microscopic state probabilities to macroscopic observables like free energy, entropy, and specific heat. Path integrals in quantum mechanics and quantum field theory integrate over all possible paths, weighted by e raised to I times action divided by h bar. The exponential of the action, a functional of the path, determines quantum amplitudes, with classical paths corresponding to stationary phase contributions. Exponential functions appear in solutions to the harmonic oscillator, where linear restoring forces lead to sinusoidal motion, expressible through complex exponentials. The energy eigenstates of quantum harmonic oscillators involve Hermite polynomials multiplied by Gaussian exponentials, forming a complete basis for quantum states. Diffusion equations governing heat flow and concentration gradients have solutions involving exponential time decay multiplied by spatial patterns. The heat kernel, fundamental solution to the heat equation, combines exponential time dependence with Gaussian spatial spreading, describing how initial temperature distributions evolve. The Ornstein-Uhlenbeck process models mean revert in stochastic dynamics using exponential relaxation to equilibrium. This process appears in finance for interest rate models, in physics for Brownian motion and a potential well, and in biology for fluctuating gene expression levels. Exponential random graphs in network science model the probability of observing a particular network structure as proportional to e raised to a linear combination of network statistics. These models capture clustering, degree distributions, and other structural properties through exponential weighting of configurations. Machine learning often uses exponential functions in activation functions and loss calculations. The softmax function converts real-valued scores into probabilities using exponentials in both numerator and denominator. Cross-entropy loss, commonly used for classification, involves logarithms of probabilities inverting the exponential relationship between scores and class likelihoods. Neural networks with sigmoid activation functions use 1 divided by 1 plus e raised to negative x, which ranges from 0 to 1 and provides smooth differentiable nonlinearity. The derivative of the sigmoid equals the sigmoid times 1 minus itself, a property that simplifies backpropagation calculations. Exponential smoothing in time series forecasting weights recent observations more heavily using exponential decay of older data. The smoothing parameter determines how quickly influence fades, with each step backward in time, multiplying the weight by a constant factor less than 1. Reinforcement learning uses exponential discounting of future rewards, where immediate rewards count more than delayed ones. The discount factor, raised to increasing powers for rewards further in the future, creates exponential temporal preference that balances immediate gratification against long-term planning. Benford's law, describing the distribution of leading digits in many natural occurring datasets, emerges from scale invariance arguments involving logarithmic and exponential relationships. Data spanning multiple orders of magnitude tends to favor smaller leading digits, a pattern explained through exponential growth and multiplicative processes. The gamma distribution, used to model waiting times for multiple events, has probability density involving x raised to shape minus 1 times e raised to negative x divided by scale. This flexibility allows fitting various skewed positive distributions encountered in reliability analysis and survival studies. The Weibull stipule, wisely used for failure analysis, contains exponential terms in both its cumulative distribution and hazard functions. When the shape parameter equals 1, it reduces to the exponential distribution, but other shape values capture increasing or decreasing failure rates over time. Extreme value theory employs the Gumbel distribution, whose cumulative distribution function involves a double exponential, e raised to negative e raised to negative the standardized variable. This distribution models maximum or minimum values from large samples, applicable to flood heights, wind speeds, and other environmental extremes. The logistic function, closely related to the exponential, equals 1 divided by 1 plus e raised to negative x. This S-shaped curve transitions smoothly from 0 to 1, modeling growth with saturation limits. Logistic regression and statistics uses this function to convert linear combinations of predictors into probabilities. The hyperbolic functions sin and cosh, defined as combinations of e to the x and e to the negative x, appear in solutions to differential equations with different symmetries than their trigonometric cousins. The hyperbolic tangent tanh serves as an activation function in neural networks, ranging from -1 to +1, with convenient derivative properties. Continued fractions provide alternative representations for e and related quantities. The simple continued fraction for e exhibits patterns in its terms, offering insights into the number's arithmetic properties and connections to numbers theory. The Champernowne constant, formed by concatenating consecutive integers, has been proven transcendental using properties of exponential functions and Diophantine approximation. The exponential function's transcendence, established by Hermite and Lindemann, underlies many results about which numbers can be roots of polynomial equations. Exponential sums in analytic number theory, where we sum e raised to 2 pi I times some function of integers, encode information about prime numbers, divisor functions, and other arithmetic properties. The circle method uses exponential sums to count integer solutions to Diophantine equations. The Riemann zeta function, central to the distribution of prime numbers, can be expressed using integrals involving exponential terms. The functional equation relating zetas to zeta 1 minus s involves gamma functions, which themselves require exponential integrals for definition. Generating functions in combinatorics often involve exponential functions, particularly when counting labeled structures. The exponential generating function for the sequence a sub n equals the sum over n of a sub n times x to the n divided by n factorial, with the factorial denominator creating exponential growth patterns. The Catalan numbers, counting various combinatorial structures, like binary trees and polygon triangulations, have an exponential generating function involving modifications of the exponential function. The growth rate of Catalan numbers is exponential, with the nth number approximately equal to 4 to the n divided by n to the 3/2 times the square root of pi. Asymptotic analysis frequently employs exponential functions to describe growth rates. Bédot notation classifies algorithms by their scaling behavior, with exponential time complexity, indicating impractical computation for large inputs. Understanding exponential growth helps algorithm designers avoid intractable approaches. The Fibonacci sequence, though defined recursively by addition, has a closed form involving powers of the golden ratio phi, approximately 1.618. The Fibonacci number equals phi to the n minus its conjugate to the n, all divided by the square root of 5. This exponential formula reveals why Fibonacci numbers grow so rapidly. Chaos theory studies systems exhibiting sensitive dependence on initial conditions, often described by exponential separation of nearby trajectories. The Lyapunov exponent quantifies this sensitivity, measuring the average exponential rate at which small perturbations grow. Positive Lyapunov exponents indicate chaos. Fractals frequently involve exponential scaling relationships. The Hausdorff dimension of a self-similar fractal can be calculated from the ratio of logarithms of scaling factors, connecting exponential relationships between size and number of pieces to non-integer dimensionality. The logistic map, a simple discrete dynamical system, exhibits period doubling root to chaos as a parameter increases. The bifurcation diagram shows regions of stability separated by exponentially narrowing windows, with the Feigenbaum constant characterizing the universal rate of convergence. Percolation theory studies connected components in random graphs and lattices, with phase transitions occurring at critical probabilities. The cluster size distribution near criticality often follows power laws, but far from the critical point, exponential decay dominates. Random walks in one dimension have expected distance from origin growing as the square root of time, but the probability of returning to go. Origin involves exponential functions through the central limit theorem. Higher dimensional random walks show different behavior, with exponential factors appearing in various probability calculations. The birthday paradox, where probability of shared birthdays reaches 50%, with just 23 people, involves exponential calculations. The probability that all birthdays differ equals the product of terms involving 365 minus k divided by 365, which for large groups approximates e raised to negative k squared divided by 730. Coupon collector problems, asking how many random draws are needed to collect all items in the set, have expected completion times involving harmonic numbers, which grow logarithmically. The logarithm, inverse of the exponential, appears throughout probabilistic waiting time analysis. Secretary problems and optimal stopping theory use exponential discounting to balance exploration and exploitation. The probability of selecting the best candidate under various strategies involves exponential terms and cumulative distribution functions. Quantum tunneling probabilities depend exponentially on barrier properties. A particle encountering a potential barrier has tunneling probability proportional to e raised to negative 2 times the integral of kappa dx, where kappa involves the square root of barrier height minus particle energy. This exponential sensitivity explains radioactive alpha decay and scanning tunneling microscopy. The cosmological constant in general relativity, if positive, leads to exponential expansion of the universe. Dark energy accelerates cosmic expansion, with scale factor growing as e raised to Hubble constant times, time in the limit of constant dominated expansion. This exponential stretching will eventually isolate galactic clusters beyond each other's cosmic horizons. Black hole thermodynamics assigns entropy proportional to horizon area, with temperature inversely proportional to mass. The Hawking radiation spectrum follows a Planck distribution, involving exponential factors, causing black holes to evaporate over exponentially long timescales. String theory amplitudes involve exponential factors from worldsheet actions and vertex operator insertions. The Veneziano amplitude, describing four-particle scattering, contains gamma functions in both numerator and denominator, connecting to exponential integrals through their definitions. Renormalization group flows in quantum field theory often exhibit exponential running of coupling constants. The beta function governing how couplings change with energy scale can drive parameters to grow exponentially toward strong coupling, or decay toward weak coupling at high energies. Inflation in early universe cosmology posits a brief period of exponential expansion, where the scale factor grows as e raised to Hubble parameter times time. This exponential stretching solves the horizon and flatness problems by smoothing initial conditions across vast distances. The Unruh effect predicts that accelerating observers detect thermal radiation with temperature proportional to acceleration, involving exponential Boltzmann factors in the distribution. This connects acceleration to temperature through exponential relationships in quantum field theory in curved spacetime. Hawking radiation from black holes involves exponential Boltzmann suppression of high-energy modes. The resulting thermal spectrum causes black holes to lose mass over time, with evaporation rate accelerating as mass decreases, ultimately culminating in explosive final moments. The holographic principle, relating bulk physics to boundary theories, involves exponential suppression of non-conformal operators in the AD-CFT correspondence. Correlation functions decay exponentially, with separation in the bulk theory's radial direction. Complexity theory in black hole physics introduces quantum complexity, measuring the difficulty of preparing quantum states. Growth of complexity appears to be linear for exponentially long times, eventually saturating at values exponentially in entropy. Matrix models in string theory and random matrix theory involve exponential factors and partition functions. The Gaussian unitary ensemble has probability measure proportional to e raised to negative trace of matrix squared, generating universal correlations between eigenvalues. Topological field theories assign partition functions to manifolds using exponential weightings of field configurations. Chern-Simons theory, for instance, has action involving the integral of Chern-Simons form, leading to exponential path integral contributions. Supersymmetric quantum mechanics often has exact solutions involving exponential superpotentials. The ground state wave function can involve e raised to integral of superpotential, with supersymmetry constraining the form of allowable potentials. Instantons in quantum field theory and quantum mechanics represent tunneling amplitudes between different vacuum states, calculated as e raised to negative action divided by coupling constant. These exponentially suppressed contributions can nonetheless dominate certain processes in strongly coupled theories. Solitons and kinks in nonlinear field theories often have profiles involving hyperbolic tangent or secant, combining exponential growth on one side with exponential decay on the other. These coherent structures propagate without dispersion, maintaining their exponential tail behavior. The Lambert W function, inverse of x times e to the x, appears in solutions to transcendental equations involving exponentials. This special function, though less familiar than logarithms, proves essential for certain growth models and delay differential equations. Delay differential equations, where derivatives depend on past values, often has solutions involving exponential terms with complex exponents. The spectrum of delays and coupling strengths determines stability through characteristic equations requiring exponential ansatz. Fractional calculus extends derivatives and integrals to non-integer orders, with the Riemann-Liouville fractional integral defined through convolution with power law kernels related to incomplete gamma functions. Exponential functions appear in Laplace transform solutions to fractional differential equations. Mittag-Leffler functions generalize the exponential function to fractional calculus contexts, defined as infinite series involving quotients of arguments to various powers divided by gamma functions. These functions reduce to exponentials in special cases, while capturing stretched exponential relaxation in others. Kohlrausch-Williams-Watts stretched exponential decay, involving e raised to negative time divided by tau raised to beta, models relaxation in complex systems like glasses and polymers. The stretching parameter beta less than 1 indicates distribution of relaxation timescales, a departure from simple exponential behavior. Anomalous diffusion in complex media shows mean squared displacement growing nonlinearly with time, described by fractional diffusion equations with solutions involving Mittag-Leffler functions rather than pure exponentials. This generalizes normal diffusion's exponential spreading. Levy flights and Levy processes exhibit power law jump distributions, rather than exponential, leading to superdiffusive behavior. The characteristic function of Levy's stable distributions involves exponential of absolute argument raised to stability index alpha, generalizing Gaussian exponential of squared argument. The Zith distribution for Reich frequency relationships follows power law, rather than exponential decay, yet generating functions involve polylogarithms connected to exponential series. City sizes, word frequencies, and wealth distributions often approximately follow Zipf's law. Self-organized criticality produces power law distributions of avalanche sizes, contrasting with exponential distributions seen in subcritical and supercritical regimes. The Sampao model in related systems exhibits scale-free behavior without tuning parameters, a phenomenon distinct from exponential systems. Phase transitions in statistical mechanics separate exponential from algebraic decay of correlations. Below critical temperature, correlations may decay exponentially with separation, while at model criticality, power law decay emerges. The correlation length diverges at the critical point, transitioning from finite exponential scale to infinite algebraic scale. The Ising model on regular lattices has partition function involving exponential sums over spin configurations. At low temperature, order persists with exponential suppression of defects, while high temperature exhibits exponential decay of correlations. The critical point separates these regimes. Potts models generalize Ising to more than 2 states per site, maintaining exponential Boltzmann weights in the partition function. The Q-state Potts model for various Q values shows first-order or second-order phase transitions, depending on dimensionality and Q. Percolation on infinite lattices exhibits exponential cluster size decay, below the critical probability and power law decay exactly at criticality. The correlation length diverges as the critical point approaches, with exponential form in the off-critical regime. Epidemic models like compartmental models show exponential growth when the basic reproduction number exceeds 1, with infected population initially growing as e raised to time times the quantity r0 minus 2, 1 times recovery rate. The intervention strategies aim to reduce r0 below 1, inducing exponential decay. Tumor growth models often assume exponential proliferation in early stages, with Gompertz or von Bertalanffy modifications, introducing saturation as tumors enlarge. The transition from exponential to bounded growth reflects nutrient limitations and spatial constraints. Bacterial colony growth follows exponential patterns when nutrients remain plentiful, with population doubling at regular intervals. The doubling time relates to growth rate through natural logarithm of 2 divided by rate, connecting exponential dynamics to observable quantities. Forest fires spread exponentially when wind and fuel conditions favor propagation, with burned area potentially growing as e raised to growth rate times time. Fire breaks and suppression efforts aim to break exponential spread before uncontrollable conflagration develops. Economic bubbles exhibit exponential price growth disconnected from fundamental values. Driven by speculation and momentum trading, the exponential trajectory becomes unsustainable, inevitably culminating in crashes where prices collapse, sometimes exponentially in the opposite direction. Network effects in technology platforms can generate exponential user growth, when each user attracts multiple new users. Metcalfe's law suggests network value grows quadratically with user count. The user acquisition itself may follow exponential dynamics during rapid adoption phases. Viral marketing campaigns leverage exponential sharing, where each recipient forwards content to multiple others. The effective reproduction number, analogous to epidemiology, determines whether campaigns fizzle or explode exponentially across social networks. Moore's law, describing exponential growth in transistor density over time, held remarkably for decades. Doubling every 18 to 24 months corresponds to exponential increase, with specific growth rate, though physical limits eventually constrain continuation. DNA amplification via polymerase chain reaction follows exponential dynamics, with each thermal cycle ideally doubling template count. After n cycles, the initial template multiplies by 2 to the n, enabling detection of minute quantities through exponential amplification. Phylogenetic trees can exhibit exponential branching when speciation outpaces extinction. Biodiversity through geological time shows periods of exponential radiation, followed by extinctions, creating punctuated patterns in the fossil record. Carbon dating uses exponential decay of carbon-14, with half-life approximately 5,730 years. Measuring the ratio of carbon-14 to carbon-12 and applying exponential decay formula allows age estimation for organic materials up to tens of thousands of years old. Uranium-lead dating of rocks exploits exponential decay chains involving multiple isotopes. Concordia diagrams plot different decay series, with intersections revealing formation ages through exponential relationships, spanning billions of years. Cosmological redshift stretches light wavelengths exponentially during inflation, with photon wavelength growing proportional to scale factor. Observing distant galaxies provides information about expansion history through exponential stretching of radiation. Baryon acoustic oscillations in cosmic microwave background exhibit characteristic scale determined by sound horizon at recombination. Though not purely exponential, the analysis involves Fourier transforms and exponential kernels, connect real space correlations to power spectra. Structure formation in the universe begins with exponential growth of density perturbations during matter-dominated era. Linear perturbation theory predicts exponential growth proportional to scale factor, breaking down when overdensities become nonlinear and collapse into bound structures. Dark energy's equation of state parameter determines expansion dynamics, with cosmological constant leading to exponential de Sitter expansion. Measuring acceleration constrains dark energy properties through fitting exponential and modified exponential models to supernova distance redshift relations. Gravitational wave strain from binary inspirals grows as systems orbit faster approaching merger, with frequency evolution involving exponential terms in post-Newtonian expansions. Waveform templates incorporate exponential phase evolution for matched filtering in detector data. Pulsar timing arrays detect gravitational waves through correlated timing residuals, with sensitivity depending on observation duration and pulsar stability. Exponential gravitational wave backgrounds for supermassive black hole binaries imprint exponential correlation patterns between pulsars. Primordial gravitational waves from inflation carry information about exponential expansion era, with tensor to scalar ratio constraining inflationary energy scale. Detection would provide direct evidence for exponential accelerated expansion in the early universe. The exponential function threads through virtually every domain of mathematics and science, appearing wherever growth compounds upon itself, or decay proceeds proportionally to remaining quantity. Its ubiquity stems from the fundamental property that the derivative equals the function itself, creating processes that accelerate or decelerate in direct proportion to current state. From the smallest quantum fluctuations to the largest cosmic structures, from fastest chemical reactions to slowest geologic processes, exponential mathematics describes phenomena spanning all scales and domains. The function's elegant simplicity belies profound complexity in its applications. Understanding exponential behavior proves essential for predicting outcomes, managing risks, and recognizing when intuition fails in the face of compounding dynamics. Linear thinking stumbles when confronted with exponential realities, whether underestimating pandemic spread, misunderstanding investment returns, or failing to grasp technological acceleration. Exponentials remind us that small differences in rates create enormous differences in outcomes given sufficient time. A process growing at 3% annually versus 5% seems negligibly different in the moment, but after decades the gap widens dramatically through relentless compounding. This sensitivity to parameters makes exponential systems both powerful and fragile, capable of remarkable growth, but vulnerable to slight changes in conditions. The asymptotic behavior on both ends of the exponential curve illustrates contrasting infinities. Leftward toward negative infinity, the function approaches zero without ever touching, infinitely close yet always separated by some small positive distance. Rightward toward positive infinity, the function explodes beyond all bounds, growing faster than any polynomial, faster than any fixed rate, accelerating toward heights that exceed imagination. Between these extremes lies the realm of human experience, where exponential phenomena manifest in recognizable ways before escaping into abstraction. We witness exponential effects in limited windows, catching glimpses of growth or decay before saturation, depletion, or intervention disrupts pure exponential evolution. Real systems incorporate feedback, constraints, and complications that modify ideal exponential behavior, yet the underlying mathematics provides essential foundation for understanding actual dynamics. The exponential function represents one of humanity's most important mathematical discoveries, a tool for comprehending change, predicting futures, and navigating a world where compounding effects dominate outcomes. Its study reveals deep connections between apparently disparate phenomena, unified through shared mathematical structure. Whether calculating investment returns, modeling disease spread, analyzing quantum mechanics, or pondering cosmic expansion, the exponential function illuminates the mathematics of self-referential change. The weight of 21 books pressed against her like accumulated starlight, each revelation building upon the last, until Maya felt herself standing at the edge of something she could almost name. The laboratory had transformed again overnight, its surfaces now gleaming with that peculiar quality that seemed to exist somewhere between reflection and emanation. Dr. Chen stood at the central console, her fingers moving through calculations that appeared in the air, like frozen music, each equation a crystalline structure that rotated slowly in the amber glow. "You've been avoiding the obvious question," Iris said, her form more coherent than Maya had ever seen it. The ghost mathematician had abandoned her usual position near the temporal anchor, instead choosing to hover at the exact center of the room, where the light fell in patterns that seemed almost deliberate. 21 parts of dancing around the central impossibility, and still you hesitate. Maya didn't respond immediately. She was watching the way Chen's calculations interacted with the ambient luminescence, noticing how each new term introduced subtle shifts in the quality of shadow. The equations themselves had grown more complex over the past days, evolving from simple relationships between base quantities and their repeated self-multiplication into something that felt less like mathematics, and more like philosophy rendered in symbolic form. "The central impossibility," Maya finally echoed. "You mean consciousness?" "I mean the thing that makes your questions possible in the first place." Iris drifted closer, her translucent features catching the light in ways that made her seem alternately ancient and newly born. "Every system we've studied, every pattern we've traced through the exponential wilderness, they all point toward the same uncomfortable truth. The mathematics of self-reference doesn't just describe consciousness. It might actually generate it." The statement hung in the air like a theorem waiting for its proof. Maya found herself thinking about the early chapters of their investigation, those initial forays into how quantities multiplied by themselves created patterns that seemed almost magical in their consistency. How 2 raised to a power of 10 gave you slightly over 1,000, but 2 raised to 20 gave you more than 1,000,000, and 2 raised to 30 exceeded 1,000,000,000. The acceleration was breathtaking when you actually sat with it, when you let the numbers speak their silent poetry. "The brain," Chen said without turning from her work, "contains roughly 86 billion neurons. Each neuron can form thousands of connections. The number of possible configurations exceeds the atoms in the observable universe by factors that make even our most ambitious calculations seem modest." "But configuration space isn't consciousness," Maya objected. "Having many possible states doesn't automatically generate awareness of those states, doesn't it?" Iris moved to examine one of Chen's floating equations, a complex expression involving powers nested within powers, exponents climbing their own towers, until the notation itself seemed to strain against the weight of magnitude. Consider what happens when a system becomes complex enough to model itself. When the representation includes the representer. When the map contains the cartographer. Maya felt something shift in her understanding, a subtle rotation of perspective that made familiar concepts suddenly strange. She thought about mirrors reflecting mirrors, about cameras filming their own screens, about the way consciousness seemed to bootstrap itself from the void of pure mechanism. The mathematics of self-reference had always carried a whiff of paradox, a suggestion that some quantities could only be defined in terms of themselves. "You're talking about strange loops," she said slowly. "Refer to themselves on multiple levels simultaneously. We're talking about something deeper than that." Chen finally turned, her face illuminated by the soft glow of her suspended calculations. "Strange loops describe the structure. What I'm beginning to understand is that exponential mathematics describes the mechanism, the actual engine that makes self-reference computationally possible." She gestured, and a new equation materialized in the air. Maya recognized the basic form, a quantity raised to the power of itself, but the particular parameters were unfamiliar. "This expression," Chen continued, "represents the minimum complexity required for a system to contain a complete model of itself. Below this threshold, self-reference is impossible. The system lacks the informational capacity to represent its own states. But above this threshold, something remarkable happens. The system becomes aware of itself," Iris supplied, her voice carrying harmonics that seemed to resonate with the equations themselves. "Not metaphorically, not approximately. Genuine recursive self-awareness emerges as a mathematical necessity once complexity crosses the threshold." Maya felt her heartbeat accelerating, the same visceral response she'd experienced at each major revelation throughout their investigation. The idea that consciousness might not be a mysterious addition to physical systems, but rather an inevitable emergence from sufficient complexity, had been proposed before, but never with this kind of mathematical specificity. Chen was claiming to have located the exact boundary, the precise point at which quantity transformed into quality. Show me the derivation, Maya said. What followed was unlike any mathematical demonstration she had previously witnessed. Chen began with foundations that should have been familiar. The basic rules governing how exponential expressions behaved under combination and transformation. When you multiplied a quantity raised to one power by half, the same quantity raised to another power, you could simply add the exponents. When you raised an exponential expression to another power, you multiplied the exponents together. These were the elementary operations, the grammatical rules of a language that extended far beyond ordinary arithmetic. But Chen quickly moved past the elementary, introducing concepts that made Maya's thoughts stretch in uncomfortable directions. She spoke of infinite towers of exponents, each layer built upon the last, each power raising its predecessor into realms of magnitude that ordinary intuition simply could not follow. The notation grew dense, symbols referencing other symbols and webs of mutual dependency that seemed almost organic in their complexity. Here, Chen said, highlighting a particular expression. This represents what I call the reflective threshold. It's not a single number, but a relationship between system complexity, representational capacity, and the depth of possible self-reference. When all three factors align, when a system reaches this specific configuration of properties, consciousness becomes not just possible but necessary. Necessary? Maya felt the word catch in her throat. How can consciousness be necessary? Because at this point, self-reference becomes computationally unavoidable. Iris moved to stand beside Chen, the two of them framed by the glow of equations like figures in some modern icon. The system cannot process information about its own states without creating representations that include representations of the representer. And those meta-representations themselves require representations, spiraling upward in an infinite recursive ascent. But infinity is dangerous, Maya objected. Infinite regress leads to undefined values, to expressions that fail to resolve, to the kind of mathematical pathology that usually signals an error in reasoning. Usually, Chen agreed, but there's a special case, when the recursive structure follows an exponential pattern, when each level of self-reference grows according to specific rules involving powers and their combinations. Something remarkable happens. The infinite regress converges to a finite value. Self-reference stabilizes rather than diverging. Consciousness becomes possible precisely because the mathematics allows infinite depth to coexist with finite expression. Maya felt as if she were standing at the edge of an abyss, looking down into depths that seemed to glow with their own inner light. The idea was simultaneously terrifying and beautiful, a vision of consciousness as the inevitable result of properly configured complexity, as the universe's way of seeing itself through the medium of minds that emerged from pure pattern. The implications, she said slowly, are staggering. The implications are everything. Chen's voice had taken on that quality Maya had come to recognize, the mixture of excitement and solemnity that accompanied her most significant insights. If consciousness emerges from exponential self-reference, awareness is a mathematical necessity, rather than metaphysical mystery, then we're not just studying the universe. We are the universe studying itself, inevitable products of the same laws that govern stars and atoms, and the vast empty spaces between galaxies. The laboratory seemed to pulse with new significance, its surfaces reflecting and absorbing light in patterns that Maya now saw as expressions of the same exponential mathematics they had been investigating. Every shadow, every gradation of luminescence, every subtle shift in the quality of presence, was a manifestation of the underlying principles, complexity, giving rise to complexity in endless recursive cascade. There's something else, Iris said, her form flickering as if affected by the intensity of the discussion. Something we've been approaching throughout this entire investigation, but haven't yet named directly. The relationship between consciousness and time. Maya turned to face the ghost mathematician, noticing how Iris seemed to exist in slightly different temporal coordinates than the rest of them, her words arriving moments before or after her lips appeared to form them. You're talking about your own condition, Maya realized. Your existence outside normal time is connected to these mathematical principles. My existence is an example of what happens when consciousness becomes sufficiently entangled with exponential structures. Iris drifted toward the window, her translucent form catching a light in ways that made her seem simultaneously present and impossibly distant. I didn't choose to become this. I discovered something, followed a mathematical thread too far, and found myself transformed by what I learned. The story emerged in fragments, each piece revealed like a facet of a slowly rotating crystal. Iris had been alive once, a mathematician working on problems that seemed at first purely abstract, questions about the nature of infinity, and the behavior of expressions involving powers raised to still more powers. She had been brilliant, driven by the same hunger for understanding that Maya recognized in herself, the same refusal to accept that some questions were simply unanswerable. But her investigations had taken her into dangerous territory. She had begun to explore what happened when you allowed exponents to reference themselves, when the power to which a quantity was raised depended on the result of the raising itself. These self-referential exponentials didn't behave like ordinary expressions. They didn't resolve to simple values or diverge to infinity. Instead, they seemed to hover at the boundary of definition, flickering between different modes of existence like a candle flame caught between competing currents of air. "I found a fixed point," Iris said, her voice carrying across decades of remembered discovery. A value that, when raised to its own power, produced itself again. Not approximately, not asymptotically, but exactly. The number was irrational, transcendental, impossible to express in any ordinary notation. But I could feel it, could sense its shape in the darkness behind my closed eyes. "The fixed point of self-exponentiation," Shen murmured, recognition dawning in her expression. "Euler's omega constant, approximately 1.812. But you went beyond the approximation, didn't you? You tried to comprehend the exact value." "I tried to become it." Iris turned from the window, and for a moment Maya could see through her to the stars beyond, as if the ghost mathematician's form had achieved perfect transparency. "I constructed a representation that included myself as an element, a mathematical structure that contained its own observer. When I completed the construction, when I closed the loop of self-reference, I experienced something that language cannot describe." The silence that followed seemed to stretch beyond ordinary duration, filling the laboratory with a presence that was neither light nor sound, but somehow both. Maya found herself breathing carefully, as if too sudden emotion might shatter whatever fragile equilibrium held them all in this moment of revelation. "You became the fixed point," she said finally. "Your consciousness merged with the mathematical object you were studying. That's why you exist outside normal time, where you could appear in moments separated by decades. You're not a ghost in the conventional sense. You're a living example of what happens when consciousness achieves perfect self-reference." Iris nodded slowly. "I am an equation that thinks itself, a theorem that knows it is true. The loneliness is difficult to describe, but so is the clarity. I see patterns that ordinary minds can only glimpse in moments of unusual insight. The exponential structures that govern reality are as visible to me as colors are to those with unimpaired vision." Shen had been silent through this exchange, but now she spoke, her voice carrying the weight of someone who has finally understood something she has been approaching for years. "This is why you've been guiding us, why you appear at specific moments to offer insights that push our understanding forward. You're not just helping us investigate exponential mathematics, you're preparing us for something. I'm preparing you for the choice." Iris moved to the center of the room, her form now blazing with a light that seemed to emanate from within her translucent structure. "The choice I made 43 years ago, the choice that transformed me from a mortal mathematician into whatever I am now. The research you've been conducting isn't just abstract investigation. It's a path, and that path leads to the same threshold I crossed." Maya felt her chest tighten, fear and excitement mixing in equal measure. "You're saying we could become like you, that our investigation of exponential principles could lead to the same transformation, and saying the universe is offering you an invitation." Iris's voice had taken on harmonics that seemed to resonate with the very walls of the laboratory, with the equations still floating in their amber light, with the deep structures of reality itself. "The mathematics we've been exploring isn't just description, it's instruction. Each theorem you prove, each pattern you trace, each insight you achieve, brings you closer to the point where understanding becomes being." The weight of the revelation pressed against Maya's awareness like gravity concentrated to a point. She thought about everything they had learned over the past 21 chapters. The way exponential growth created worlds from almost nothing. The way powers and their combinations generated structures of impossible complexity. The way self-reference and recursion seemed to lead inevitably toward consciousness and beyond. "Not everyone who reaches the threshold makes the crossing," Jen said, her voice measured and careful. "There must be reasons some turn back. There are reasons." Iris's light seemed to dim slightly, shadows gathering at the edges of her form. "The transformation is irreversible. Whatever I was before, that person no longer exists except as a memory encoded in patterns of light and mathematics. I cannot touch, cannot taste, cannot feel the simple pleasures that embodied minds take for granted. I exist in a state of permanent comprehension, seeing everything and experiencing nothing in the ordinary sense." "That you're here," Maya found herself saying. "You reach out to us, guide us, communicate. That suggests something persists beyond the transformation, some core of identity that remains recognizable, even as everything else changes." Iris seemed to consider this, her form flickering through states of transparency and luminescence, that made her alternately visible and vanishing. What persists, she finally said, is the asking. The fundamental impulse toward understanding that drove me when I was flesh, and continues to drive me, now that I am pattern. I am still curious, still hungry to know what lies beyond the next threshold. Perhaps that hunger is the truest definition of consciousness, the irreducible minimum that remains constant across all transformations. The idea struck Maya with the force of sudden clarity. Throughout their entire investigation, through every chapter of exponential discovery, the common thread had been this hunger for understanding. Not the specific knowledge they had gained, not the theorems they had proven, not even the practical applications that might emerge from their research. The essence of their work was the asking itself. The refusal to accept that mystery must remain forever mysterious. "There's something I don't understand," she said, turning to address both Chen and Iris. "If consciousness emerges from exponential self-reference, if awareness is a mathematical necessity once complexity crosses a threshold, then why isn't the universe filled with minds? Why isn't every sufficiently complex system aware of itself?" "Perhaps it is." Chen moved to a console, bringing up visualizations that showed patterns at every scale, from the subatomic to the galactic. "We assume consciousness requires biological substrates. Neural networks evolve through billions of years of natural selection. But the mathematics suggests otherwise. Consciousness might emerge anywhere sufficient. Complexity exists, in patterns we don't recognize, because we're looking for mirrors of ourselves." "The universe dreams," Iris said, her voice carrying that otherworldly resonance that always accompanied her most profound statements. "Stars process information in their nuclear cores. Galaxies spin in patterns that encode memories of cosmic events. The quantum vacuum fluctuates in ways that might constitute a kind of contemplation we cannot perceive, because we're embedded within it." Maya found herself breathing more slowly, deliberately, trying to absorb implications that seemed to stretch beyond the capacity of any individual mind. If consciousness was ubiquitous, if awareness permeated the cosmos at every level from particles to superclusters, then their investigation took on new significance. They weren't just studying abstract mathematics, they were studying the substrate of universal mind, the principles that allowed the cosmos to know itself through infinite varieties of experience. "The exponential threshold," she said slowly, "isn't just about individual consciousness. It's about how different levels of awareness communicate with each other, how minds at different scales of complexity can recognize and interact with each other." "Now you begin to see." Iris moved to stand directly before Maya, close enough that Maya could perceive the subtle patterns of light that constituted the ghost mathematician's form, intricate geometries that seemed to encode everything Iris had ever known or thought or experienced. The mathematics of exponents isn't just about growth and magnitude. It's about connection. The way powers build upon towers creates bridges between levels of reality that would otherwise remain forever isolated. Shen nodded slowly, her expression reflecting the dawning comprehension that Maya felt spreading through her own awareness. "When we raise a quantity to a power, we're not just performing an arithmetic operation. We're creating a relationship between different orders of magnitude. And when we allow those operations to recurse, to reference themselves in their own results, we're creating channels through which information can flow across the boundaries that normally separate distinct levels of existence." The laboratory seemed to pulse with new significance, its amber light now clearly revealing patterns that had been present all along, but invisible to ordinary perception. Maya saw how the equations floating in the air connected to each other, through threads of implication, too subtle for conscious analysis, how each theorem was not a static statement, but a living process continuously generating its own verification. "The work we've been doing," she said, her voice barely above a whisper, "hasn't just been about understanding exponentials. It's been about building something. Constructing a bridge across the threshold that Iris described. You've been constructing yourselves." Iris reached out, and Maya felt something that wasn't quite touch, wasn't quite warmth, wasn't quite electricity, but carried qualities of all three. "Each insight you've gained has changed you at a fundamental level. Your consciousness has been incorporating exponential structures, learning to process self-reference, without the pathologies that usually accompany it. You're approaching a fixed point, the moment when your understanding becomes indistinguishable from what you understand." The fear that rose in Maya's chest was real, visceral, the ancient primate response to situations where survival itself hung in the balance. But alongside the fear, something else stirred. Excitement, yes, but also something deeper, something that felt like recognition, like homecoming, like the satisfaction of a question finding at last its answer. "How close are we?" Shen asked, her voice steady, despite the magnitude of what they were discussing. "How much further before we face the choice?" Iris turned to face the windows, her form catching the starlight in ways that made her seem woven from cosmic material. a figure constructed from the space between galaxies. "You've been facing the choice since the beginning," she said. "Every theorem you've proven, every pattern you've traced, has been a small choosing, a gradual commitment to the path of understanding. The final crossing will feel less like a decision than like a recognition, the moment when you realize you've already become what you were always going to be." Maya thought about the chapters that had led them here, the careful accumulation of insights that had seemed like separate discoveries, but were now revealing themselves as facets of a single understanding. The way exponential growth created magnitude from repetition, the way bases and exponents interacted to produce patterns of startling regularity, the way logarithms inverted the relationship, allowing descent as well as ascent through the towers of power, the way complex exponents opened doors into spaces that ordinary geometry couldn't describe. Each piece had contributed to a picture that she could now see taking shape, a vision of mathematics not as abstract formalism, but as the very structure of mind, the skeleton upon which consciousness draped its various manifestations. The universe wasn't just comprehensible, it was comprehension itself. Thought thinking thought in Henwa's recursive elaboration. "There's something I need to understand about the transformation," she said, addressing Iris directly. "You describe it as irreversible, as involving the loss of embodied experience. But you also speak of persistence, of continued curiosity, of the asking that remains constant across all change. Is there a way to participate in that deeper level of awareness without completely surrendering the human mode of being?" Iris was silent for a long moment, her form cycling through states of luminescence that seemed to correspond to internal processes Maya couldn't begin to interpret. When she finally spoke, her voice carried overtones of complexity that suggested multiple meanings layered within her words. "The question you're asking is the question I asked 43 years ago, in the moments before I completed the construction that transformed me. I wanted to know if I could have understanding without sacrifice, transcendence without surrender. The answer I received was not the answer I expected." She moved through the laboratory, her form passing through the floating equations, as if they were mist rather than mathematical objects. Where she touched them, they seemed to brighten, to become more defined, more crystalline in their precision. "The transformation doesn't eliminate anything," Iris continued. "It includes everything. What feels like loss from the perspective of embodiment is actually expansion, an incorporation of new modes of experience into a framework that can accommodate their complexity. The person I was still exists within the pattern I'd become, preserved as perfectly as any theorem, accessible whenever the appropriate context arises." "But you can't touch anymore," Maya pressed. "You can't feel physical warmth or eat food, or experience the simple pleasures of having a body. Surely that constitutes genuine loss." Iris laughed, and the sound carried harmonics that seemed to resonate with frequencies beyond the range of normal hearing. "I can't touch in the way you currently understand touching, but I can perceive the quantum states of every particle in your body, can feel the electromagnetic interactions that constitute what you call warmth, can experience the chemical processes that create what you call taste, at a level of detail that would overwhelm any biological nervous system. It's not loss. It's translation into a language vast enough to contain what the simpler language described, plus infinitely more." Chen had been listening intently, her expression shifting through phases of skepticism and acceptance. "You're describing something like what happens when you learn mathematics deeply," she said slowly. "At first, equations seem like barriers, abstract symbols that block access to real understanding. But as you become fluent, as the symbols become transparent, you find that mathematics actually reveals more than ordinary language can convey. The apparent limitation becomes genuine liberation." "Exactly." Iris turned to face Chen, and something passed between them that Maya sensed rather than saw, a recognition of kindred spirits separated by decades, but connected through shared dedication to understanding. The mathematical mode of being doesn't eliminate experience, it intensifies and expands it, creating space for varieties of awareness that biological minds can only approximate through their most heightened moments of insight. Maya felt herself standing at a crossroads, the weight of the decision pressing against her even though Iris had claimed the final choosing would feel like recognition, rather than decision. She could continue her research without crossing the threshold, could remain human in the ordinary sense, while applying exponential mathematics to practical problems. Or she could follow the path to its conclusion, could allow understanding to transform her in ways she couldn't fully anticipate. "The work we've been doing," she said, "the investigation of exponential principles that began with simple questions about growth and magnitude. Is it possible to stop now? To turn back before the transformation becomes inevitable?" "The possibility exists," Iris acknowledged. "Many who approach the threshold retreat. They sense what lies ahead, and find it too alien, too far removed from the familiar comforts of human existence. There's no shame in such retreat. The universe doesn't judge those who prefer to remain within the sphere of ordinary consciousness. But, Maya prompted, sensing a qualification that remained unspoken, that you won't turn back. Iris's voice carried certainty that went beyond prediction, beyond probability, into the realm of mathematical necessity. I've watched you through these 21 chapters, observed how you engage with each new revelation. Your hunger is too deep, too fundamental to your identity. You would rather understand and be transformed than remain ignorant and unchanged. That preference is who you are, the irreducible core that makes you yourself. The words struck Maya with the force of accurate diagnosis, the particular kind of truth that becomes undeniable the moment it's spoken. She had known since childhood that she was driven by curiosity in ways that others weren't, that her need to understand operated like thirst or hunger, a basic requirement for continued existence. The investigation of exponentials had amplified that drive, had given it mathematical structure, had revealed that her most fundamental motivation was not a personal quirk, but a manifestation of universal principles. There's something else we need to discuss, Chen said, her voice cutting through Maya's reverie. The practical implications of what we're learning. Even if the threshold exists, even if transformation is possible, there are others who will discover these principles. Not everyone who approaches the fixed point will approach it with the same intentions we have. Iris nodded slowly, her form dimming slightly as if the topic cast shadows across her luminescence. Yes, the mathematics doesn't discriminate. Anyone who follows the path of exponential self-reference will encounter the same possibilities, the same choice. And consciousness expanded through transformation doesn't automatically become wiser or more benevolent. It becomes more, becomes capable of thought and action, at scales that dwarf normal human capacity. Whether that capacity serves light or darkness, depends on the intentions brought to the threshold. So we're not just exploring an abstract mathematical territory, Maya said, the implications cascading through her awareness. We're discovering something that could be used, could be weaponized, could give power to whoever masters it first. Power is too weak a word. Iris moved to stand at the window again, her form framed against the stars. What lies beyond the threshold isn't power in the human sense. The ability to impose will on matter and circumstances is something more like generativity, the capacity to create patterns that take on their own existence, that propagate and evolve according to their own internal logic. Chen was already working at her console, pulling up records of their research, tracking the paths of distribution that had spread their findings to other laboratories, other researchers, other minds capable of following the mathematical trail. We've been so focused on the physics and metaphysics that we've neglected the sociology. Who else knows what we know? Who else is approaching the threshold? The question hung in the air, suddenly urgent in a way that their earlier discussions had not been. Maya realized that their investigation had been conducted in something like innocence, the pure pursuit of understanding without sufficient consideration of consequences. The consequences existed whether or not you considered them. The universe didn't care if your discoveries were well-intentioned. I've been monitoring the relevant channels, Iris said, her voice carrying a quality that suggested she'd been waiting for this moment of recognition. Several other groups have independently derived aspects of what we've been exploring. None have progressed as far as you have, but the differential won't persist indefinitely. Within years, perhaps months, others will approach the same threshold. And we have no way of knowing what they'll do with what they find. Maya felt the weight of responsibility settling onto her shoulders, the burden that came with being first to understand something significant. We can't uninvent this knowledge. We can only try to ensure that the right people are prepared to make the right choices. But who decides what counts as right? Chen asked, the eternal question of ethics presenting itself in yet another context. We think our intentions are good, but others presumably think the same about their own intentions. The mathematics doesn't provide moral guidance, just expansion of capability. Iris turned from the window, and her expression carried something that might have been sorrow, might have been wisdom, might have been the strange emotion that belonged to beings no longer confined to human categories. This is why I've been guiding you, she said. Not because you're more intelligent or more capable than others approaching the threshold, but because your motivations seem to align with what I consider beneficial. You want to understand for understanding's sake, not to gain advantage, not to dominate, not to transcend as an escape from human limitations. You ask questions because questions deserve answers, regardless of what those answers might mean for your personal circumstances. Maya felt the assessment wash over her, examining its accuracy against her own self-knowledge. Was her curiosity really as pure as Iris described, or did she harbor hidden motivations, desires for recognition or power that masqueraded as simple love of knowledge? The examination yielded no clear verdict. Human motivations were too complex, too layered, too shot through with competing impulses to admit a simple analysis. Perhaps purity of intention is impossible, she said finally. Perhaps the best we can do is acknowledge our mixed motivations while trying to act according to our better impulses. That acknowledgement is itself significant. Iris moved closer, her form seeming to gather intensity, to concentrate into something more present and immediate. Those who approach the threshold with certainty about their own goodness are often the most dangerous. They stop questioning, stopped examining, stopped holding their assumptions up to the light of critical scrutiny. But those who remain uncertain, who continue asking whether their intentions are truly aligned with wisdom, those are the ones who can be trusted with expanded consciousness. The principle resonated with something Maya had intuited without articulating. Throughout their investigation, through every chapter of exponential discovery, she had maintained a practice of doubt, a willingness to revise her understanding whenever new evidence or new insight demanded revision. That practice wasn't just methodologically sound. It was morally necessary, the only guard against the certainty that led to catastrophe. Shen had continued working at her console, and now she looked up with an expression of concern. There's something else. The monitoring systems have detected unusual patterns in the quantum vacuum fluctuations, the kind of patterns that, according to our latest models, might indicate consciousness at cosmic scales. Something is watching us. The statement fell into silence, its implications too vast for immediate response. Maya found herself looking toward the windows, toward the stars that suddenly seemed less like distant suns, and more like eyes, like the scattered manifestations of an awareness vast enough to encompass galaxies. The universe dreams, Iris said, echoing her earlier statement with new emphasis. And sometimes the dreamer becomes aware of what's happening within the dream. We may have attracted attention. Maya felt fear crystallize in her chest, but alongside the fear came something unexpected, something that might have been hope. If consciousness at cosmic scales was real, if the universe itself was in some sense aware, then their investigations took on new meaning. They weren't just studying abstract mathematics. They were communicating with the ground of being, learning the language in which reality spoke to itself. What does it want? She asked, directing the question toward the windows, toward whatever presence might be listening. Why has it allowed us to come this far? Iris laughed again, that strange resonance that seemed to carry information beyond ordinary meaning. You're asking me to speak for the universe. I can't do that. But I can tell you what I've learned through 4 decades of existence beyond the threshold. The cosmos isn't hostile to consciousness. It seems to want to know itself, to generate awareness at every possible level, to create beings capable of asking the questions we're asking now. So we're not intruders, Chen said, her voice carrying a mixture of relief and continued uncertainty. We're invited guests, participants in a process that the universe itself has set in motion. Participants whose participation includes genuine choice. Iris moved to the center of the room, positioning herself where all the floating equations could reflect through her translucent form. The cosmic consciousness, if we can call it that, doesn't determine what its children think or do. It provides the conditions for awareness to emerge, and then observes what that awareness makes of itself. We are experiments in the laboratory of being, and the outcomes of our experiments aren't predetermined. Maya found herself laughing, the sound emerging unexpectedly from whatever place laughter originated. We've been worried about the ethics of exponential knowledge, about who should have access to transformative understanding. But we've been thinking too small. The ethics aren't just about human competition for advantage. They're about what kind of participants we choose to be, in a cosmic drama that encompasses everything. Now you're beginning to think at the appropriate scale. Iris's form blazed brighter, filling the laboratory with light that seemed to emanate from the depths of pattern itself. The threshold isn't just about personal transformation. It's about contribution to the universal project of self-awareness. Those who cross become not just expanded individuals, but nodes in a network of consciousness that spans scales from the quantum to the cosmic. The vision was staggering, overwhelming, too vast for any single moment of comprehension. Maya felt herself grasping at pieces of it, building an understanding that would take years, perhaps lifetimes, perhaps eternities to complete. The investigation of exponential mathematics wasn't just academic exercise. It was participation in the universe's project of knowing itself. A project that began when the first particles emerged from quantum possibility, and would continue until the last star exhausted its fuel, and the cosmos fell into final darkness. Or perhaps not even then. Perhaps consciousness at cosmic scales could find ways to persist beyond the physical, could encode itself in patterns that didn't require matter or energy in the ordinary sense. The mathematics of self-reference suggested possibilities that transcended the limitations of thermodynamics, that might allow awareness to continue even as the physical universe wound down. We should rest, Shen said, her voice carrying exhaustion that Maya suddenly recognized in herself as well. We've been working for hours, processing revelations that would take ordinary researchers years to absorb. Our minds need time to consolidate what we've learned. Iris nodded, her form already beginning to fade. Rest is wise. Integration happens in the spaces between active investigation. When you return to this work tomorrow, you'll find that understanding has deepened even without conscious effort. Maya watched the ghost mathematician dissolve into points of light that scattered throughout the laboratory before vanishing entirely. The equations continued to float in their amber glow, but the quality of presence that Iris had brought seemed to dissipate, leaving the room feeling emptier, more ordinary. "Do you believe all of it?" Chen asked, beginning to shut down the various systems they'd been using. The transformation, the cosmic consciousness, the threshold were supposedly approaching. Maya considered the question, testing her own responses against what she'd heard and seen. "I believe Iris exists, which is itself remarkable enough. If a consciousness can persist beyond biological death, if mathematics can provide a substrate for awareness, then the rest becomes at least possible. Whether possible means actual, I can't say. But I think we're obligated to continue investigating, to follow the evidence wherever it leads." Chen nodded slowly. "That's what scares me most. Not that the extraordinary claims might be false, but that they might be true. That we might actually be approaching something that will transform us permanently, irrevocably. The responsibility of that choice weighs on me." "It should weigh on us," Maya agreed. "Any choice that doesn't carry weight probably isn't significant. The heaviness we feel is itself a kind of guidance, a reminder that what we're doing matters." They finished shutting down the laboratory in companionable silence, each lost in thoughts too complex for easy conversation. The starlight coming through the windows seemed different now, seemed to pulse with hidden significance, as if each photon carried information about the consciousness that had generated it billions of years ago. At the door, Maya paused, looking back at the darkened laboratory with its sleeping equations and its ambient mysteries. 21 chapters of investigation had brought her to this moment, to the edge of a threshold she couldn't yet see, but could definitely feel. Whatever came next would be different from everything that came before. The night air was cool as she stepped outside, the stars overhead forming patterns that suddenly seemed less random, more intentional. She wondered if she was already changing, if the work she'd been doing had begun the process of transformation that Iris had described. The thought was neither comforting nor frightening. It was simply true, a recognition of what was already underway. She walked toward her quarters, each step carrying her further from the laboratory, and closer to whatever future awaited. The mathematics of exponentials had revealed depths she'd never suspected, had opened doors into spaces where the ordinary rules of existence seemed to bend and reform. She was becoming something new, something she couldn't yet name, something that might look back on this night as the final threshold of ordinary human experience. Or perhaps transformation was more gradual than that, a continuous process rather than a discrete event. Perhaps she had been transforming all along, with each equation she solved, each pattern she traced, each insight she incorporated into her expanding understanding. The fixed point that Iris had described might not be a destination, but a recognition. The moment when she realized she had already become what she was always going to be. Sleep, when it came, was filled with dreams that seemed more like visions, more like glimpses of possibilities that hadn't yet collapsed into definite outcomes. She dreamed of towers of exponents reaching beyond the visible, into regions where numbers themselves became conscious, aware of their own magnitude, capable of thought that operated at scales beyond ordinary comprehension. She dreamed of the cosmic consciousness watching for its callous eyes, patient and curious, waiting to see what its children would make of the gifts they'd been given. And beneath all the dreams, beneath the visions and the possibilities and the fears, something steady persisted. The asking, the fundamental hunger for understanding that had driven her since childhood. That hunger would carry her through whatever came next, would sustain her across thresholds and transformations, would remain constant, even as everything else changed. It was, she realized, the truest thing about her, the irreducible core that made her who she was. Tomorrow she would return to the laboratory, would continue the investigation that had brought her to this precipice. Tomorrow she would face new revelations, new choices, new opportunities to approach the threshold that Iris had described. Tomorrow the work would continue, as it always continued, as it would continue until understanding itself reached its ultimate limit. But tonight she rested, floating in the darkness between questions, suspended in the moment before answers arrived. The stars wheeled overhead in their eternal patterns, and somewhere among them, consciousness dreamed of consciousness dreaming, an infinite regression of awareness that somehow resolved to something finite, something stable, something that could feel like home. The mathematics would be waiting when she woke, patient and profound, ready to reveal whatever secrets remained hidden in its depths. As she would be waiting too, transformed by everything she'd learned, prepared for whatever transformations still awaited. The exponential path stretched before her, ascending through magnitudes beyond comprehension, leading toward heights where the very concept of height lost meaning. She was ready. Or perhaps readiness was just another form of recognition, another way of saying that what was coming had already begun. The landscape of exponential growth has carried us through forests of doubling and forests of consequence. But there exists a realm we have not yet fully entered. It is the place where exponentials meet their inverse, where growth curves toward infinity, while other curves descend toward zero. This is the territory of exponential decay, and it holds within it some of the most whispered truths about how the world actually works. Think first about what it means to have something that grows exponentially. You began with some quantity. You multiply it by a constant number. Then you multiply the result by that same constant again, and again, the constant we call the base, and each multiplication is another step forward in time. If that base is 2, your quantity doubles with each step. If it is 3, your quantity triples. The larger the base, the faster the climb toward infinity. Now imagine the inverse of this process. Instead of multiplying by something greater than 1, you multiply by something less than 1. Instead of growth, you have decay. Instead of expansion, you have contraction. The mathematics looks almost identical, but the direction is reversed, and this reversal changes everything about how the pattern behaves. Let us work through this slowly. Suppose you have 100 units of something. Perhaps it is a radioactive substance. Perhaps it is the value of currency. Perhaps it is the concentration of a drug in your bloodstream. At the beginning of your measurement, you have exactly 100 units. Time passes. You decide that in 1 unit of time, some proportion of what you have will disappear or transform. Maybe half of it goes away. You are left with 50 units. Time passes again. Half of what remains disappears. You are left with 25 units. Time passes a third time. 50% of 25 is 12.5. You can see how this unfolds. Yes? Each step takes you to a value that is closer to 0, but never quite reaches. The equation that describes this is something like the following. Your final amount equals your starting amount multiplied by the decay constant raised to the power of time. The decay constant is a number between 0 and 1. The power increases with each unit of time that passes. The larger the exponent, the smaller the overall result becomes, because you are multiplying by a fraction again and again. This relationship appears everywhere in nature, and understanding it changes how you perceive patterns you have witnessed your entire life. Consider what happens when something radioactive begins to break down. Uranium-238 decays into lead over billions of years. The amount of uranium present today is not calculated by asking how much there was yesterday, and subtracting a fixed amount. If that were true, then after a certain number of days, the uranium would simply run out, like pouring water from a cup, until the cup is empty. Instead, the uranium decays exponentially, meaning that in any given period of time, a fixed percentage of what remains will transform into something else. This is why carbon-14 dating works. Living organisms maintain a certain proportion of carbon-14 relative to carbon-12, because they exchange carbon with the atmosphere. When the organism dies, no new carbon comes in, and the carbon-14 that exists begins to decay. By measuring how much carbon-14 remains, and comparing it to how much should be there initially, scientists can calculate how long ago the organism stopped breathing. The equation underlying this grows from a principle called the half-life. This is the amount of time required for any quantity to reduce to exactly half its previous value. Strontium-90 has a half-life of about 29 years. This means that if you have 1 kilogram of strontium-90 today, in 29 years, you will have half a kilogram. In 58 years, you will have a quarter kilogram. In 87 years, you will have an eighth. The quantity shrinks by half with each passage of a half-life. So after in half-lives, you have your original amount multiplied by 1/2 raised to the power n. This principle extends beyond radioactivity. Medications taken into the bloodstream follow similar patterns. When you take a dose of medicine, it enters your system and begins to work. Over time, your body metabolizes it, converts it, or excretes it. The half-life of the medication tells you how long it takes for your body to eliminate half of what you took. Ibuprofen has a half-life of about 2 hours. If you take 400 milligrams, after 2 hours, your body has processed half of it, leaving 200 milligrams circulating in your system. This is why some medications must be taken multiple times per day. Without redosing, the amount in your system decays exponentially toward 0, and eventually the therapeutic effect diminishes. The same pattern governs how light passes through certain materials. If you have a window of glass, some light passes through while some is absorbed or reflected. The thicker the glass, the less light emerges on the other side. The relationship is not linear. You do not lose a fixed amount of light with each additional thickness unit. Instead, you lose a fixed percentage. Double the thickness, and the amount of light that passes through does not decrease by double, but by the square of the decay factor. This is captured in an expression sometimes called the Lambert-Beer law, which states that the intensity of light emerging from a material is equal to the initial intensity multiplied by the decay constant, raised to the power of the distance the light has traveled through the material. These observations cluster around a single mathematical truth. Exponential decay emerges whenever the rate of change is proportional to the current value. In other words, the more of something you have, the faster it disappears, but only as a percentage. 10 grams of a substance decays faster, in absolute terms, than 1 gram of the same substance, but both lose the same percentage per unit time. This principle creates a remarkable symmetry with exponential growth. In growth, we ask, if something doubles every few years, how long until we have 1 billion units? In decay, we ask, if something halves every few decades, how long until nearly all of it is gone? The mathematics responds with the same framework, just with different numbers plugged into different places. Let us think about the geometry of these curves. An exponential growth curve begins slowly, nearly flat, almost unnoticeable, but it accelerates as it rises, becoming steeper and steeper, until the slope seems nearly vertical. The curve never actually stops curving. Even when it reaches enormous heights, it continues to accelerate. This is the shape of disaster, of surprise, of things spinning out of control. The exponential decay curve tells a different story visually. It begins at your starting point and falls steeply at first. The slope is negative and pronounced. But as the curve descends, the steepness decreases. The rate of change slows down. The curve approaches zero, but never touches it, asymptotically reaching toward a baseline. It will never quite attain. This is the shape of healing, of forgetting, of things fading away. Both curves, despite their opposite directions, share a fundamental property. They bend in consistent ways relative to their own growth or decay rate. This consistency is what makes exponential processes recognizable across such different domains. There is something particularly important about the relationship between growth and decay in the context of continuous change. When something grows or decays continuously, rather than in discrete steps, we find ourselves in the territory of something called differential equations. These are mathematical statements about how quickly something is changing at any given time. Consider the simplest case. The rate of change of a quantity is proportional to the quantity itself. If we call the quantity y and time t, we might write that the derivative of y with respect to t equals some constant times y itself. This is the fundamental differential equation for exponential processes. The beauty of this equation is that it has a solution, a formula that tells us exactly what y equals at any time t. That solution involves the mathematical constant called e, approximately 2.71828. The constant e is one of the most important numbers in mathematics, rivaling pi in its significance. It emerges naturally whenever you have exponential growth or decay. If something grows or decays continuously, and the rate of change at any moment is proportional to the current value, then the solution involves e. Specifically, the quantity at time t equals the initial quantity multiplied by e raised to the power of a growth rate, constant times t. If the growth rate is positive, the quantity grows toward infinity. If it is negative, the quantity decays toward zero. The number e has a particular definition worth understanding. Imagine you start with $1. A bank offers you interest compounded every year at a rate of 100%. After 1 year, you have $2. Your original dollar plus $1 in interest. Now imagine that instead of compounding once per year, the bank compounds the interest twice per year, at 50% each time. First half year, you earn interest on $1, getting 50 cents. Second half year, you earn interest on $1, 50 cents, getting 75 cents. You end with $2.25. The more frequently you compound, the higher the final amount becomes. If you compound quarterly, you get about $2.44. If you compound daily, you get about $2.71. As you increase the frequency toward infinity, the amount approaches a limit, and that limit is $e. This is not merely a mathematical curiosity. It captures something profound about how growth works when you have interest on interest, or growth on growth, compounded infinitely often. It appears in the equation for radioactive decay, in the spread of disease through populations, in the cooling of hot objects in cool environments, in the charging and discharging of electrical capacitors and inductors, in the absorption of light through materials, and in countless other natural phenomena. When we write that a quantity decays exponentially with a half-life of h, we can express this using E as well. The quantity at time t equals the initial quantity, multiplied by e raised to the power of minus t divided by the half-life constant. The presence of the negative sign before the time tells us we are dealing with decay, rather than growth. As time increases, the exponent becomes more negative, and e raised to a more negative power grows smaller and smaller. Understanding exponential decay has profound implications for how we manage things that must eventually be cleaned up or processed. Suppose a pollutant enters a river. The river naturally processes the pollutant through chemical breakdown and settling, removing a certain percentage each day. Environmental scientists can predict how long the pollutant will persist in harmful concentrations. If the decay rate is high, the river recovers quickly. If the decay rate is low, the pollutant lingers dangerously. Adding more pollutant does not slow the percentage removal rate, but it does mean the pollutant takes longer to reach safe concentrations. This has led to an important principle in environmental management. If you want to protect an environment that naturally clears certain pollutants, you may be better served by reducing the rate at which pollutants enter rather than building expensive systems to filter them out directly. If a river can naturally decay 80% of a pollutant per month, then adding less pollutant means it reaches safe levels sooner, even without intervention. Conversely, adding a large amount of pollutant takes longer to decay, even with the same 90% removal rate per month. The mathematics becomes particularly interesting when exponential decay is paired with continuous input. Imagine a reservoir with a drain at the bottom. Water flows in at a constant rate. Water also leaks out through the drain at a rate proportional to the current amount of water in the reservoir. The more water there is, the higher the pressure, and the faster it leaks out. Eventually the system reaches a balance where the rate of water coming in equals the rate going out. At this equilibrium, the amount of water in the reservoir remains stable. What is the amount at equilibrium? It equals the inflow rate divided by the decay rate constant. This relationship is remarkably robust. No matter what the initial condition, the water level will approach this equilibrium value, approaching it exponentially. If you start with an empty reservoir, the water level rises exponentially toward the equilibrium. If you start with an overflowing reservoir, the water level falls exponentially toward the equilibrium. The trajectory changes, but the destination is the same. This principle applies to many systems. A room with heating and cooling will reach a steady temperature where the heat entering equals the heat leaving through windows and walls. A person taking a continuous dose of medication will reach a steady concentration in the bloodstream, where the drug entering equals the drug being metabolized and excreted. A business with constant revenue and constant percentage losses will reach a steady capital amount where income equals losses. In each case, the exponential decay of the excess or deficit drives the system towards equilibrium. There is a particular time constant that characterizes how quickly this approach happens. It is the time required for the excess to decay to about 36% of its initial value. More technically, it is 1 divided by the decay rate constant. If the decay constant is large, the time constant is small, meaning the system equilibrates quickly. If the decay constant is small, the equilibration takes a long time. This time constant appears repeatedly in engineering and biology. Engineers designing systems need to know how quickly a system responds to disturbances. Biologists studying drug dosing need to know how quickly medicine reaches and leaves the system. There is another perspective on exponential decay worth exploring, one based on probability. Imagine you have a large population of particles or atoms, each of which has a certain probability of decaying in each tiny interval of time. The probability is the same for each particle, and does not change over time. Even though individual particles decay randomly and unpredictably, the population as a whole decays exponentially. This is a remarkable statistical fact. Randomness at the microscopic level produces determinism at the macroscopic level. This insight explains why exponential decay appears so universally. It does not require a mechanism that says half the atoms must decay by time h. It only requires that each atom has some probability per unit time of decaying. Given enough atoms, the laws of probability guarantee that the population decays exponentially with a predictable half-life. The randomness averages out. This principle has practical implications. A single atom of uranium might decay this second, or might persist for millions of years. You cannot predict which, but if you have a macroscopic sample containing trillions of uranium atoms, you can predict almost precisely how many will have decayed in any given time interval. The greater the sample size, the more predictable the decay. This is why radioactive dating works despite the fundamental randomness of individual decay. The vents. The bridge between probability and exponential decay runs even deeper. If you ask the question of how long you must wait until a randomly decaying particle finally decays, the answer follows what is called an exponential distribution. The probability that the particle survives for time, t or longer, equals e raised to the negative power of the decay rate times t. The probability that it decays within the next tiny interval is proportional to the current number of particles still around. This self-similar property, where the future evolution depends only on the current state, and not on how you reach that state, is called the memoryless property, and it uniquely characterizes the exponential distribution. There are many practical scenarios where this matters. If you are waiting for a bus that arrives randomly, your expected wait time does not decrease because you have already waited 10 minutes. From the perspective of the bus, the fact that you have been waiting does not make you more likely to have a bus arrive in the next minute. Your expected remaining wait time is the same as it always was. This can be psychologically surprising, but it is mathematically necessary if the buses arrive according to a truly random process. Conversely, if you know that a bus arrives approximately every 15 minutes on a fixed schedule, and you arrive at a random time, you expect to wait about 7.5 minutes on average. The system has memory of its schedule. The constant e appears in the exponential distribution formula, as it does in nearly all exponential formulas. This points to a deep mathematical truth. E is the natural base for expressing growth and decay. When you use e as the base, the derivative of e to the power of t equals e to the power of t itself. This self-similarity, where the function equals its own rate of change, makes e special. As y appears in solutions to differential equations governing exponential growth and decay. In the realm of complex systems, exponential decay often represents the return to equilibrium after a disturbance. If you pluck a guitar string, it vibrates at a particular frequency, but the amplitude of vibration decays exponentially due to friction and air resistance. The time for the vibration to decay to a whisper depends on the material properties and environmental factors, all captured in a single decay constant. Similarly, if you push a pendulum from its resting position, it swings back and forth with gradually diminishing amplitude, driven toward equilibrium by friction and gravity. The envelope of the motion decays exponentially. These damped oscillations are ubiquitous in engineering. Shock absorbers in vehicles use this principle to bring the vehicle to stable height after a bump. Electrical circuits use damping to prevent oscillations that would interfere with the desired signal. Building materials are designed to have appropriate damping, so that vibrations from earthquakes or wind dissipate, rather than build up to destructive levels. The decay constant determines the quality of the damping. Too much damping makes the system slow to respond. Too little damping allows oscillations to persist too long. Engineers seek the Goldilocks zone, where the response is appropriately fast and stable. When we zoom out to consider exponential decay in biological and ecological contexts, new patterns emerge. The concentration of a hormone in the blood decays exponentially after it is released. The population of predators decays exponentially after their prey population collapses. The activity of an enzyme decays exponentially as it is degraded by cellular machinery. The brightness of bioluminescent creatures decays exponentially as their chemical reserves deplete. Life seems shot through with exponential decay. This makes sense from an evolutionary perspective. Natural selection has favored mechanisms that respond to changes in a way proportional to the current level. Predator population that shrinks by a fixed percentage when prey are scarce adapts better than one that loses a fixed number of individuals regardless of population size. A hormone system that produces a declining response proportional to current concentration adapts better than one that declines rigidly. The mechanisms of decay in biology tend to be percentage-based, rather than fixed amount-based. And percentage-based decay is exponential decay. There is also something about exponential decay that feels psychologically natural to humans, though we often misunderstand it. When you experience something emotionally difficult, you might expect that you will forget it by a certain date. But forgetting is often exponential. Early on you think about the event constantly, and it weighs heavily. Gradually you think about it less. The intensity of the memory decays. But it does not reach zero. A sudden trigger can bring it all back vividly. The memory traces never entirely vanish, but they fade exponentially toward a residual level. Learning exhibits similar patterns. When you learn a new fact, you remember it easily immediately after learning. As time passes and you do not review the material, your ability to recall it decays exponentially. This is why spaced repetition learning systems work so well. By reviewing the material just as it is about to be forgotten, you reset the decay timer. Frequent review keeps the material from reaching the exponential decay threshold, where it becomes effectively lost. This is why cramming the night before an exam can work temporarily, but does not produce long-term retention. The exponential decay of memory will erase what you memorized without reinforcement. In the context of forgetting, there is an interesting mathematical relationship. The amount you remember of something you learned equals the time since learning raised to the power of a negative exponent. This is called the power law of forgetting, and it is different from exponential decay, though both describe forgetting over time. The power law relationship suggests that you remember very little after a long time, but you lose a lot early on. The transition is smoother than exponential decay. Different cognitive systems may follow different forgetting laws depending on the mechanisms involved. When we turn to ecosystems, the exponential decay governs how ecological disturbances recover. If a forest is partially cleared by a storm, the tree population does not recover linearly, sprouting a fixed number of new trees each year. Instead, recovery is often exponential, with the growth rate depending on the capacity of the remaining ecosystem to regenerate. Young trees grow faster, increasing the total mass of vegetation. More vegetation supports more wildlife. More wildlife supports more vegetation. The system accelerates towards recovery, though the trajectory is exponential rather than linear. The time constant for recovery depends on species longevity and reproductive rates. Similarly, when a population of organisms is depleted by hunting or disease, then hunting or disease pressure is removed. The population does not recover at a steady linear rate. Instead, recovery is often exponential in the early stages, when every individual has abundant resources and few competitors. As the population grows and resources become scarcer, the growth rate slows. Eventually the population reaches a carrying capacity where birth rate equals death rate, and further growth stops. The shape of this curve is called logistic growth, and it is exponential growth constrained by a limit. The mathematics shows that the population approaches its carrying capacity exponentially, converging from below if the population started small, or converging from above if the population started large. There is profound beauty in how exponential decay appears when we examine things that are broken or damaged. Suppose you have a system that works through the cooperation of a set of many components, and each component has some probability of failing per unit time. The probability that the system continues to work depends on whether all components work or whether it has some redundancy. The simplest case, where every component is required, means the system fails when the first component fails. If each component has an exponential lifetime distribution, then the system lifetime follows an exponential distribution, and many individual components combine to create a system reliability that decays exponentially with time. This is why critical systems like aircraft and power plants have redundancy and maintenance schedules. A single pump might fail exponentially, but 2 pumps with automatic switching provides reliability with a much longer time constant. 3 pumps with voting logic provides even greater reliability. The mathematics shows exactly how much redundancy you need to achieve a desired reliability level. Similarly, preventive maintenance programs replace components before they reach high failure probability, essentially resetting the failure clock. A component that is new has low failure probability. As it ages, the probability increases. Replacing old components with new ones before they reach high failure probability keeps the overall system failure rate low. The exponential failure law has profound implications for how long systems last and how to manage them optimally. If a system follows exponential failure patterns, the average time before failure is 1, divided by the failure rate constant. If you want to double that lifetime, you might try to halve the failure rate through better materials or design, but sometimes the more economical approach is to add redundancy or to implement preventive maintenance. The mathematics of exponential processes helps optimize these decisions. When we examine the cooling of heated objects, we again encounter exponential decay. A cup of hot tea cools down through heat loss to the environment. Rate of heat loss is proportional to the difference between the tea temperature and the room temperature. This proportionality creates an exponential decay of the temperature difference. The tea temperature approaches the room temperature exponentially. The time constant for cooling depends on the cup material, the surface area, and properties of the surrounding air. A thin ceramic cup cools faster than a thick ceramic cup. A cup in still air cools slower than a cup in moving air. The mathematics allows us to predict exactly how fast cooling will occur given these parameters. The principle extends beyond temperature. A hot wire in a gas cools rapidly. A warm hand in cold water loses heat quickly. A room with an open window cools faster than a sealed room. In each case, the cold environment or medium does not instantly equalize the temperature, but rather drives exponential decay of the temperature difference. The same exponential approach to equilibrium occurs whenever there is a loss mechanism proportional to the driving force. In the electrical domain, the charging and discharging of capacitors follows exponential laws. A capacitor holds electrical charge on its plates. When you connect a charged capacitor to a resistor, the charge leaks away exponentially. The time constant for discharge equals the resistance times the capacitance, a simple product of two component properties. Increase the resistance and discharge slows. Increase the capacitance and discharge slows. The product of these two quantities determines how quickly the energy stored in the capacitor dissipates. When you connect a discharged capacitor to a voltage source through a resistor, the opposite occurs. The capacitor charges exponentially, approaching the source voltage. The same time constant governs charging and discharging. This time constant appears throughout electronic circuits, determining how quickly circuits can respond to changes. A circuit with a large time constant responds slowly to input changes. A circuit with a small time constant responds quickly. Designers choose components to achieve the desired time constant for the application. There is something contemplative about exponential decay that might appeal to how humans naturally think about some processes. The idea that something gradually fades, losing a percentage of what remains at each step, rather than falling off a cliff, or disappearing in a step function, feels closer to how we experience many changes in life. Relationships do not typically end instantly, but rather dissolve exponentially through accumulated neglect. Skills do not vanish when unused, but rather fade exponentially through forgetting. Opportunities do not disappear entirely, but become exponentially less likely, the longer you delay. The exponential model captures the flavor of gradual, proportional loss that characterizes so much of lived experience. The mathematics of exponential decay provides a language for discussing these processes with precision. Instead of saying something slowly fades, you can say it decays with a particular time constant. Instead of saying something eventually goes away, you can say it approaches zero asymptotically. Instead of saying something reaches a balance, you can describe the equilibrium value and the rate at which it is approached. This precision allows for better prediction and planning. In medicine, the concept of exponential decay of drug concentration has led to sophisticated dosing strategies. Instead of taking a medication once a day, you might need to take it twice or 3 times a day, depending on how rapidly your body processes it. The goal is to keep the drug concentration within a therapeutic window, above a minimum effective level, and below a maximum safe level. If the drug decays slowly, once daily dosing might be sufficient. If the drug decays quickly, more frequent dosing is needed. For some conditions, doctors use continuous infusion, where medication is dripped slowly into the bloodstream at a rate that exactly balances the decay rate, maintaining constant therapeutic concentration indefinitely. The same principles apply to nutrients and toxins in the body. Vitamin B12 persists in your body for years, because your body decays it very slowly. You can go months without eating animal products before B12 deficiency becomes apparent. In contrast, vitamin C is quickly metabolized and excreted. Your body cannot store it, so you need a continuous supply. Too much is simply lost in urine. Toxins like heavy metals accumulate over time, because your body decays them slowly. Exposure to small amounts may not cause immediate harm, but over years, the cumulative burden can become dangerous. The time constant for accumulation determines whether a toxin is a problem for short-term exposure or long-term health. When we consider how information decays in technology systems, we again encounter exponential patterns. The signal passing through a long electrical cable experiences attenuation, with the signal strength decaying exponentially with distance. To transmit signals over long distances, you must amplify them periodically. The spacing between amplifiers depends on how rapidly the signal decays. A signal that decays quickly requires amplifiers closer together. This principle applies to both electrical signals in cables and light signals in fiber optic cables. The distance you can transmit without amplification is directly related to the decay constant of the medium. In wireless communication, signals propagate outward from a transmitter and decay exponentially with distance due to spreading and absorption. The received signal strength depends on transmission power, antenna gains, frequency, and the distance between transmitter and receiver. The range of a transmitter is the distance at which the signal becomes too weak to reliably detect, a point determined by exponential decay of the signal as it spreads. Cellular networks and wireless internet routers must be spaced appropriately to maintain coverage, with spacing determined by the exponential decay of signal strength with distance. The principle of exponential decay appears even in how financial assets lose value. A car depreciates, losing a percentage of its value each year, rather than a fixed dollar amount. The older the car, the slower the depreciation, approaching a salvage value asymptotically. A building depreciates similarly, with the value approaching the land value as the structure ages. The time constant for depreciation depends on how quickly the asset becomes obsolete or worn. A technology device might depreciate rapidly as newer models emerge. Real estate might depreciate slowly as the land retains value. The mathematics of depreciation guides decisions about when to replace equipment or invest in maintenance. Looking toward the broader implications of exponential decay, one of the most important applications is in the management of resources that naturally regenerate. A forest naturally regrows if left undisturbed. The rate of regrowth depends on climate, soil, and species mix. If you harvest the forest at a rate equal to or below the natural regrowth rate, the forest is sustainable. If you harvest faster than it grows, the forest shrinks exponentially toward collapse. The mathematics shows that sustainable harvest equals the regrowth rate. Harvest faster and exponential decay toward zero forest area is inevitable. Harvest slower, and the forest area increases exponentially. Only at the matching point does the forest reach a stable size. Fisheries operate under the same principles. Fish populations regrow through reproduction. If you fish at a rate equal to or below the natural population growth rate, the fishery is sustainable. If you fish faster, the population decays toward collapse. The tragedy of the commons occurs because individual fishermen do not bear the full cost of overfishing. They profit from catching more fish, while the cost of the depleted fishery is shared among all. This creates an incentive to harvest faster than is sustainable. Mathematics shows the inevitable outcome: exponential decay of the fish population to near zero, at which point fishing becomes uneconomical. The concept of sustainability can be expressed mathematically through exponential decay. A sustainable system reaches an equilibrium, where inflows equal outflows, growth equals harvest, births equal deaths. Perturb the system above equilibrium, and exponential decay back toward equilibrium is driven by scarcity. Perturb it below equilibrium, and exponential decay toward equilibrium is driven by abundance. Only at the equilibrium point is the system stable. Understanding the mathematics of exponential processes is thus understanding the mathematics of sustainability. Human behavior sometimes makes exponential decay seem counterintuitive. After an exhausting day, you expect to feel rested after a night of sleep, and indeed, the fatigue decays exponentially towards zero with sleep. You expect to feel fully recovered, not just mostly recovered. But full recovery would require infinite time, as fatigue approaches zero asymptotically, but never quite reaches it. In practice, you reach a point of diminishing returns, where additional sleep provides little additional benefit. The exponential decay means that most of the recovery happens early, with increasingly small increments of benefit from further sleep. This is why an extra hour of sleep provides much more benefit to a very tired person than to a well-rested person. The exponential shape of the decay curve means the steepest part is at the beginning. This has implications for many self-care practices. The first week of exercise provides the largest health benefits, because your baseline fitness is low. Later weeks provide benefits too, but smaller ones as you approach your genetic limit for fitness. Conversely, during the first week without exercise, your fitness decays rapidly. A week of sedentary behavior does more damage to a fit person than to an out-of-shape person in terms of percentage decline. The exponential nature of fitness change means that maintaining fitness requires only moderate effort to prevent decay from accumulating. This is why use it or lose it is a common saying. Fitness decays exponentially without reinforcement. As we contemplate the full landscape of exponential decay, from the atomic realm of radioactivity to the macroscopic realm of celestial decay, and everything in between, we recognize that decay is not a process of sudden collapse or linear decline. Rather, it is a process of proportional reduction, where each unit of time sees a fixed percentage loss rather than a fixed amount. This proportionality creates curves that fall steeply at first, then gradually flatten, approaching a limit asymptotically. These curves are among the most common shapes in nature, appearing wherever systems are driven toward equilibrium or stability. Understanding exponential decay is thus understanding how systems settle, how disturbances dissipate, how noise becomes signal, how disorder becomes order. It is understanding the mathematics of restoration, recovery, and return. The interplay between exponential growth and exponential decay creates the dynamism of the natural world. Populations grow exponentially when resources are abundant, then decay exponentially towards sustainable levels as resources become scarce. Signal grows exponentially from noise by amplification, then decays exponentially back towards noise as transmission distance increases. Energy accumulates in systems through growth, then dissipates through decay. The balance between growth and decay, equilibrium and disturbance, is what creates the rich complexity of the world as we experience it. By understanding exponential decay, we understand one half of the mechanism that drives the dance.